If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. What lies beyond the edge of the observable universe? Have you ever wondered what lies beyond the shimmering boundary of the observable universe? This question has haunted humanity for centuries as we gaze into the cosmos and confront the limits of our understanding. What is out there in the vast expanses we cannot see or measure? Is it simply more galaxies, or is there something fundamentally different awaiting discovery? To begin unraveling this mystery, we must first understand the edge itself, a horizon dictated not by physical walls, but by the speed of light and the age of the universe. The observable universe is defined by how far light has traveled since the beginning of time, roughly 13.8 billion years ago. Light, though astonishingly fast, is not instantaneous. This limitation creates a boundary we call the cosmic horizon, a sphere roughly 93 billion light-years in diameter. Everything within this bubble is visible to us, but what about beyond? Scientists speculate on a variety of possibilities, each more tantalizing than the last. One prevailing idea is that the universe stretches infinitely beyond what we can see. If this is true, then the observable universe is merely a tiny fraction of an endless expanse filled with galaxies, stars, and other cosmic wonders. Imagine standing on the shoreline of an infinite ocean, unable to glimpse its other side. The implications of such an infinite cosmos are staggering. It could mean there are other regions, far removed from ours, where the laws of physics might vary, where gravity behaves differently, or where the constants that govern reality are unfamiliar. Another hypothesis suggests the universe may be finite but unbounded, like the surface of a sphere. In this model, traveling far enough in one direction could theoretically bring you back to where you started, much like circumnavigating the Earth. This raises the possibility that what lies beyond our observable horizon might eventually connect back to what we already know, creating a cosmic loop that challenges our linear perceptions of space. Then there's the idea of multiverses, parallel realities existing beyond our observable limits. Some scientists theorize that the edge of the universe is not a physical boundary, but a transition point to other universes, each with its own rules, dimensions, and forms of matter. If multiverses are real, our universe might be one bubble among countless others in a grander structure known as the multiverse. This idea is as exhilarating as it is unsettling, as it suggests our universe is not unique, but one of many, each possibly teeming with its own version of life. But could there be something even more mysterious than galaxies or other universes awaiting us? Some physicists propose that the true nature of what lies beyond might be a realm of pure energy or a higher dimensional space we cannot yet comprehend. String theory, for instance, postulates the existence of extra dimensions curled up so tightly they elude our detection. If we could somehow breach the observable boundary, we might find ourselves in a domain where space and time behave in unimaginable ways. There's also the intriguing possibility that what lies beyond our observable universe isn't distant in the traditional sense, but exists in a different state altogether. The concept of holographic principles suggests that our universe might be a projection from a higher dimensional reality. If this is the case, the edge of our universe might not mark the end of space, but instead be a barrier to another form of existence entirely. Cosmologists have also pondered the implications of inflation, the rapid expansion of the universe shortly after the Big Bang. This expansion might have created regions so distant from us that their light will never reach Earth. These unobservable regions, often referred to as the inflationary multiverse, could contain entirely separate pocket universes with their own unique cosmic events and histories. While this idea remains speculative, it challenges our understanding of space, time, and the scale of creation itself. The deeper we delve into the question of what lies beyond, the more we confront the limits of human perception and imagination. Our tools, though advanced, can only take us so far. Telescopes like the James Webb Space Telescope offer glimpses into the early universe, but they cannot pierce the veil of the cosmic horizon. Yet, even in the face of such boundaries, the human spirit persists. We theorize, hypothesize, and dream of ways to transcend these limits. Perhaps future technologies will allow us to bypass these constraints. Some scientists speculate that advanced civilizations might already have developed methods to peer beyond the observable universe, using quantum entanglement or wormholes to gain insights into the unknown. If such technologies exist, they could revolutionize our understanding of the cosmos and reveal secrets we can barely fathom today. Ultimately, the question of what lies beyond the observable universe is not just a scientific one. It's philosophical. It challenges our understanding of existence, forcing us to confront whether we can ever truly comprehend the infinite. As we peer into the cosmos and ponder its secrets, we are reminded of our own smallness and the vast potential for discovery that still lies ahead. Could it be that the answers are already within our grasp, waiting for the right breakthrough? Or will the secrets of what lies beyond remain forever shrouded in mystery? The edge of the observable universe might not be the final frontier, but merely the beginning of an even greater journey into the unknown. The mysterious forces shaping galaxies. What unseen forces sculpt the grand, spiraling arms of galaxies or bind their stars into cohesive structures? Galaxies, those magnificent islands of light scattered across the cosmos, are not just randomly assembled collections of stars, gas, and dust. Instead, they are intricate masterpieces shaped by a delicate balance of forces, some visible, others hidden in the fabric of the universe itself. What are these forces, and how do they guide the evolution of these colossal cosmic structures? At first glance, gravity appears to be the principal architect of galaxies. From the smallest star clusters to the largest galactic superstructures, gravity weaves its invisible threads, drawing matter together. In the early universe, minute fluctuations in the density of matter caused some regions to collapse under their own gravitational pull. Over billions of years, these collapsed regions became the seeds of galaxies. But gravity, as powerful as it is, does not work alone. Something far more enigmatic contributes to the formation and stability of galaxies: dark matter. Dark matter, an unseen and elusive form of matter, makes up approximately 27% of the universe. Yet it remains one of science's greatest mysteries. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, rendering it invisible to our telescopes. Its presence is inferred through its gravitational effects. Without dark matter, galaxies as we know them could not exist. Observations reveal that the visible mass of stars and gas in galaxies cannot account for the immense gravitational forces holding them together. Dark matter forms a sort of scaffolding, providing the extra mass needed to stabilize these structures and enabling the stunning spiral arms of galaxies like the Milky Way to persist. But how does dark matter interact with galaxies during their formation? One theory suggests that dark matter clumps together in massive halos, creating gravitational wells into which gas and dust flow. Over time, these materials condense and ignite, giving birth to stars. This dark matter halo acts as a protective cocoon, shielding the galaxy from disruptive external forces and maintaining its structure over billions of years. Yet, the true nature of dark matter remains elusive. Is it composed of undiscovered particles? Or is it a manifestation of physics we don't yet understand? Adding another layer of complexity, galaxies are influenced by a force much larger in scale: dark energy. While dark matter holds galaxies together, dark energy drives the expansion of the universe, pushing galaxies apart. This cosmic tug-of-war shapes the large-scale structure of the universe, determining how galaxies cluster and form superstructures like filaments, walls, and voids. These enormous formations, some stretching billions of light-years across, reveal the universe's grand design. Yet, their existence raises more questions than answers. How do these vast cosmic structures influence the behavior of individual galaxies? And how do the forces of dark matter and dark energy coexist to create such an intricate balance? The role of supermassive black holes adds another piece to the galactic puzzle. At the heart of nearly every large galaxy lies a supermassive black hole, often millions or billions of times more massive than the Sun. These gravitational giants influence their galaxies in profound ways. For instance, as matter falls toward a supermassive black hole, It forms an accretion disk that generates powerful jets of energy, spewing material outwards at nearly the speed of light. These energetic outbursts can regulate star formation by heating surrounding gas or expelling it entirely, preventing new stars from forming. In this way, supermassive black holes act as galactic regulators, shaping the evolution of their host galaxies over time. Galactic collisions and mergers also play a critical role in the cosmic ballet of galaxy formation. When galaxies collide, as the Milky Way and Andromeda are predicted to do in about 4.5 billion years, their shapes are distorted, and their stars are thrown into chaotic orbits. Yet, these events are not purely destructive. The collisions can trigger bursts of star formation, as gas clouds are compressed and ignited by the gravitational forces at play. Over time, these violent interactions can result in entirely new galactic forms, such as elliptical galaxies, which lack the elegant spirals of their predecessors but embody their own unique beauty. While gravity, dark matter, and collisions are central to shaping galaxies, the role of magnetism is an often overlooked factor. Magnetic fields, though weak on a galactic scale, influence the movement of charged particles, guiding the flow of gas and shaping the formation of stars. These fields, though subtle, provide an additional layer of complexity to the already intricate processes that govern galaxies. How these magnetic forces arise and evolve within galaxies remains an area of active research, but their presence suggests that the universe is even more interconnected than previously thought. Galaxies are not isolated entities. They exist within a dynamic cosmic ecosystem. Surrounding them are streams of gas, dust, and smaller satellite galaxies, all interacting through gravitational forces. These interactions can strip away material, fueling the growth of some galaxies while starving others. The interplay between galaxies and their environments reveals that they are not merely passive objects drifting through space, but active participants in a cosmic network. One of the most intriguing questions is whether these forces have an ultimate purpose. Are galaxies simply a natural consequence of the universe's physical laws, or do they play a larger role in a grander cosmic narrative? The presence of dark matter and dark energy suggests that much of what shapes galaxies lies beyond our current understanding. Every new discovery reveals not just answers, but deeper mysteries, reminding us of the boundless complexity of the cosmos. As we uncover more about the forces shaping galaxies, we are faced with yet another question. Are these forces constant across time and space, or do they evolve? If the laws of physics differ in distant parts of the universe, then the galaxies beyond our observational reach might be entirely unlike those we know. What would such alien galaxies look like, and what could they teach us about the cosmos? These mysteries continue to drive astronomers and physicists to push the boundaries of exploration and technology. Each galaxy, whether a sprawling spiral or a dense elliptical, tells a story written by gravity, dark matter, and the enigmatic energies of the universe. As we strive to understand these stories, we edge closer to answering the profound question: what are the forces that truly govern the cosmos, and how do they shape the universe's ultimate destiny? Dark energy, the universe's silent accelerator. What is the mysterious force causing the universe to expand at an ever-increasing pace? For decades, scientists believed the universe's expansion, set into motion by the Big Bang, would eventually slow down due to gravity. Yet in the late 1990s, a groundbreaking discovery revealed the opposite. The universe's expansion is not decelerating, it's accelerating. This phenomenon is attributed to an enigmatic force known as dark energy, a name that captures its elusive and unknown nature. But what is dark energy, and how does it silently govern the fate of the cosmos? To grasp the concept of dark energy, we must first revisit the fabric of space itself. Einstein's general theory of relativity teaches us that space is not a static void, but a dynamic entity that can stretch, bend, and evolve. The discovery of the accelerating universe suggests that space is infused with a form of energy that exerts a repulsive force, counteracting gravity on cosmic scales. Unlike any energy we understand, dark energy operates as if space itself has an inherent pressure, pushing galaxies apart and stretching the universe faster with each passing moment. The story of dark energy begins with the study of distant supernovae, exploding stars so luminous they can be seen billions of light years away. By observing these cosmic lighthouses, astronomers can measure the rate of the universe's expansion across time. When these observations revealed that galaxies were moving apart faster now than they had in the past, it upended long-held assumptions about the cosmos. Something unknown was accelerating the universe's growth, defying the attractive pull of gravity. This something became known as dark energy. But what could dark energy actually be? One possibility is that it is the cosmological constant, a term first introduced by Einstein himself. When Einstein developed his equations of general relativity, he included a factor to counterbalance gravity and create a stable, static universe. However, after Edwin Hubble's discovery of the expanding universe in the 1920s, Einstein abandoned the cosmological constant, calling it his greatest blunder. Ironically, modern observations suggest that a form of the cosmological constant might be real, an intrinsic property of space that drives the acceleration we now observe. If dark energy is indeed the cosmological constant, it would imply that the energy density of space remains uniform across time and space. This raises profound questions. Why does space contain this energy? Is it a fundamental feature of the universe? Or does it arise from deeper, unknown physics? Some theories propose that dark energy is linked to the quantum vacuum, a seething ocean of virtual particles that pop in and out of existence. According to quantum theory, even the emptiest vacuum is not truly empty, but brims with ephemeral energy. Could this energy be responsible for the universe's acceleration? Other explanations for dark energy point to dynamic fields that evolve over time. Unlike a static cosmological constant, these fields, often referred to as quintessence, could change their strength as the universe ages. If quintessence exists, it would imply that dark energy might not remain constant but could weaken or grow stronger in the future. Such variability could dramatically alter the universe's ultimate fate, making quintessence a tantalizing area of investigation. Still, some scientists challenge the very framework within which dark energy is understood. What if the observed acceleration is not caused by dark energy, but instead by a misunderstanding of gravity itself? Modified gravity theories propose that on the largest scales, gravity might behave differently than predicted by Einstein's equations. If true, the need for dark energy might vanish, replaced by a more comprehensive understanding of gravity's role in shaping the cosmos. The effects of dark energy are not confined to the distant reaches of the universe. They permeate all of space, influencing everything from the clustering of galaxies to the cosmic microwave background, the faint afterglow of the Big Bang. By studying these phenomena, astronomers hope to uncover dark energy's nature and its impact on the cosmos. Yet, despite its pervasive influence, dark energy remains frustratingly difficult to study directly. It does not emit light or interact with matter in any observable way, leaving scientists to infer its presence through indirect evidence. The stakes of understanding dark energy are colossal. Its discovery fundamentally altered our understanding of the universe, revealing that nearly 70% of the cosmos is composed of this invisible force. Alongside dark matter and ordinary matter, dark energy completes the trifecta of cosmic components, yet it dominates the universe's energy budget. How can something so vast and influential remain so enigmatic? Dark energy also holds the key to predicting the universe's ultimate destiny. If dark energy continues to drive acceleration, galaxies will drift further apart, and the universe will grow colder and more isolated over trillions of years. This bleak scenario, known as the Big Freeze, envisions a cosmos where stars burn out, leaving behind a dark, desolate expanse. Alternatively, if dark energy's strength increases over time, it could lead to a big rip where the fabric of space itself is torn apart, disintegrating galaxies, stars, and even atoms. On the other hand, if dark energy were to weaken or reverse, the universe's expansion might halt, leading to a big crunch where everything collapses back into a singularity. Amid these chilling possibilities, the quest to understand dark energy continues to inspire hope and innovation. Cutting-edge missions like the Euclid Space Telescope and the Vera C. Rubin Observatory are poised to deliver unprecedented insights into the nature of cosmic acceleration. By mapping the distribution of galaxies and tracing the history of the universe's expansion, these projects aim to shed light on dark energy's mysterious properties. Yet, as with any profound discovery, each answer about dark energy seems to spawn more questions. Could dark energy be connected to the multiverse, with each universe possessing its own unique value for this force? Is dark energy a transient phase in the universe's evolution, or is it a permanent feature of reality? And perhaps most intriguingly, what does dark energy reveal about the nature of space, time, and the fundamental laws governing existence? Dark energy challenges not only our understanding of the cosmos, but also our place within it. By unveiling the silent force accelerating the universe, we glimpse the vast, interconnected fabric of creation, a tapestry woven with mysteries yet to be unraveled. As we continue this cosmic journey, the question remains, will we ever fully grasp the power of dark energy, or will it forever remain a silent force shaping the universe from the shadows? The hidden symphony of cosmic microwave background radiation. Have you ever thought about what echoes remain from the universe's birth? The cosmos has a memory, a faint but persistent whisper of its fiery origin that resonates across the vast expanse of space. This whisper, known as the cosmic microwave background (CMB), is a relic from the Big Bang, a snapshot of the universe when it was just 380,000 years old. It is not merely a static image, but a symphony of light and energy, a treasure trove of information that holds the secrets of the cosmos' earliest moments. But what does this ancient radiation reveal, and how does it continue to shape our understanding of the universe? The CMB was discovered by accident in 1965, when two scientists, Arno Penzias and Robert Wilson, stumbled upon a mysterious noise while calibrating a radio antenna. This faint, pervasive static turned out to be the afterglow of the Big Bang, stretched into microwaves as the universe expanded. Its discovery revolutionized cosmology, providing irrefutable evidence that the universe had a hot, dense origin and has been cooling and expanding ever since. Imagine the universe in its infancy, a chaotic sea of particles, photons, and energy, too dense and hot for light to travel freely. During this early epoch, the cosmos was opaque, a glowing plasma where photons constantly collided with electrons. As the universe expanded, it cooled enough for protons and electrons to combine, forming neutral hydrogen atoms. This event, called recombination, allowed light to finally escape, spreading throughout the universe and creating the CMB. What we see today in the CMB is a snapshot of that pivotal moment, frozen in time. But the CMB is more than just a relic of the past. It is a cosmic map, rich with subtle patterns and variations that tell a profound story. These variations, or anisotropies, are minute differences in temperature and density across the early universe. While the CMB appears nearly uniform, detailed measurements reveal tiny fluctuations, differences of mere millionths of a degree. These fluctuations are the seeds from which all cosmic structures, from stars to galaxies, eventually grew. The significance of these patterns cannot be overstated. They encode the initial conditions of the universe, revealing clues about its composition, age, and geometry. For instance, by studying the CMB, scientists determined that the universe is 13.8 billion years old, and that it is flat rather than curved. The CMB also confirms the existence of dark matter and dark energy, invisible forces that make up 95% of the cosmos yet elude direct detection. How do we extract such precise information from the CMB? It involves an interplay of theory, observation, and advanced technology. Satellites like COBE, WMAP, and Planck have been pivotal in mapping the CMB with increasing accuracy. These missions measured the faint ripples in the CMB and translated them into a wealth of cosmological data. The Planck satellite, for instance, produced a map so detailed that it revealed evidence of primordial gravitational waves, ripples in spacetime created during the universe's rapid inflationary phase shortly after the Big Bang. Inflation is a cornerstone of modern cosmology, a theory that proposes the universe underwent an exponential expansion in the tiniest fraction of a second after the Big Bang. The CMB provides critical evidence for this theory. The uniformity of the CMB across vast distances is best explained by inflation, which would have stretched and smoothed the cosmos to its present state. The tiny fluctuations we see in the CMB are thought to originate from quantum fluctuations during this inflationary epoch, magnified to cosmic scales. Yet, the CMB also raises profound questions. One puzzle is the so-called cold spot, a region of the CMB that is significantly cooler than expected. This anomaly could be a statistical fluke, or it might hint at something far more exotic, such as the imprint of another universe or a large void in the cosmic structure. Similarly, the axis of evil, a peculiar alignment of certain CMB features, challenges our assumptions about the universe's isotropy, or uniformity in all directions. The CMB's power lies not only in what it reveals about the past, but also in how it guides our exploration of the future. It serves as a benchmark for testing new theories and models of the universe. For instance, researchers are using the CMB to search for evidence of cosmic strings, hypothetical defects in spacetime that could have formed during the early universe. Detecting such features in the CMB would revolutionize our understanding of fundamental physics. The study of the CMB is also intricately connected to dark matter and dark energy. By analyzing the CMB's anisotropies, scientists can trace the distribution of matter in the early universe, providing insights into how dark matter shaped the cosmos. Similarly, the CMB's detailed patterns reveal how dark energy influenced the universe's expansion over time. These connections highlight the CMB's role as a bridge between the known and the unknown, offering a pathway to understanding the invisible forces that dominate the cosmos. Despite its age, the CMB continues to evolve in subtle ways. As it travels through the universe, it interacts with massive structures like galaxy clusters, experiencing shifts in energy. These interactions, known as the Sunyaev-Zel'dovich effect, allow astronomers to study the distribution of matter on large scales. Additionally, gravitational lensing distorts the CMB's path, providing a unique window into the influence of gravity across cosmic distances. Yet, the most profound aspect of the CMB is its reminder of our cosmic origins. It is a direct link to the beginning of everything, a faint glow that has traveled billions of years to reach us. Each photon in the CMB carries the story of the universe's infancy, a time when all matter and energy were concentrated in a singular, fiery state. To study the CMB is to connect with the very fabric of existence, to glimpse the raw potential that gave rise to stars, galaxies, and life itself. As we continue to probe the CMB, we are left with a question that transcends science. What does it mean for us to be part of this cosmic story? The CMB reminds us that we are not separate from the universe, but deeply woven into its tapestry. It is both a mirror and a mystery, reflecting our origins while inviting us to explore the unknown. Are we alone? The hunt for extraterrestrial life. Have you ever gazed at the stars and wondered if someone, somewhere, might be looking back? This question has fueled humanity's imagination for millennia, and today it drives some of the most advanced scientific research on Earth and beyond. Are we truly alone in the universe? Or is life a cosmic inevitability, scattered across countless worlds waiting to be discovered? The search for extraterrestrial life is no longer confined to science fiction. It is a serious scientific endeavor that combines astronomy, biology, chemistry, and even philosophy. But where do we begin, and what are the chances of finding life beyond Earth? The search for extraterrestrial life starts with understanding the conditions that make life possible. On Earth, life thrives in environments ranging from scorching deserts to freezing polar ice caps, demonstrating its incredible resilience. However, all known life forms share one crucial requirement: liquid water. Water provides the medium for chemical reactions essential to life, making its presence a primary indicator of a potentially habitable environment. Consequently, much of the search for extraterrestrial life focuses on finding worlds where liquid water exists or once flowed. Our solar system alone offers tantalizing possibilities. Mars, with its ancient riverbeds and polar ice caps, has long been a candidate for hosting past or present life. Recent discoveries of underground lakes and methane plumes on Mars add to the intrigue. Methane, in particular, is a potential biosignature, as it can be produced by microbial life. Could Mars harbor underground microbial colonies, shielded from its harsh surface environment? Future missions like NASA's Perseverance rover and the European Space Agency's ExoMars rover aim to uncover clues. Beyond Mars, the icy moons of the outer planets present some of the most promising locations for extraterrestrial life. Europa, a moon of Jupiter, is covered by a thick layer of ice, beneath which lies a vast ocean kept liquid by tidal heating. Similar conditions exist on Saturn's moon Enceladus, which ejects plumes of water vapor and organic compounds from its subsurface ocean through cracks in its icy crust. These oceans may contain the energy sources and chemical building blocks necessary for life. Missions like the Europa Clipper and potential future explorations of Enceladus seek to probe these alien oceans for signs of biology. Moving beyond our solar system, the discovery of exoplanets has revolutionized the search for life. Over 5,000 exoplanets have been confirmed to date, and many more await verification. Among these are a subset known as potentially habitable exoplanets, which reside in the habitable zone of their stars, the region where temperatures could allow liquid water to exist on a planet's surface. Planets like Proxima Centauri b and TRAPPIST-1e, orbiting stars relatively close to Earth, have captured scientists' attention as possible homes for alien life. However, determining habitability involves more than finding the right temperature. Factors such as a planet's atmosphere, magnetic field, and geological activity play critical roles in supporting life. For example, a thick atmosphere can provide a stable climate and protect against harmful radiation, while a magnetic field shields a planet from solar winds that could strip away its atmosphere. Advances in telescopes, such as the James Webb Space Telescope, are allowing scientists to analyze exoplanet atmospheres for potential biosignatures. Chemical compounds like oxygen, methane, or even industrial pollutants that could indicate the presence of life. The search for extraterrestrial life is not limited to microbes or primitive organisms. The possibility of intelligent life elsewhere in the universe raises profound questions about our place in the cosmos. The search for extraterrestrial intelligence, SETI, focuses on detecting signals from advanced civilizations. Using powerful radio telescopes, SETI scientists scan the skies for patterns that could indicate artificial signals, such as repeating pulses or structured messages. Despite decades of searching, no definitive signals have been found, but this does not deter researchers. The vastness of the universe means we have only scratched the surface in our efforts to find intelligent life. One intriguing avenue in the search for intelligent extraterrestrial life is the concept of technosignatures. These are signs of advanced technology that might be detectable from Earth, such as the heat signature of megastructures like Dyson spheres, hypothetical constructs built to harness the energy of a star. Recent observations have even explored anomalies, like the unusual dimming of Tabby's star, as potential technosignatures, though natural explanations have often prevailed. Nevertheless, the search continues, driven by the idea that detecting an advanced civilization would profoundly alter our understanding of the universe. The question of alien life also prompts us to consider the forms it might take. Life on Earth is carbon-based, relying on DNA and water as essential components. But could life elsewhere be based on entirely different chemistries, such as silicon or ammonia? Astrobiologists explore these possibilities by studying extremophiles, organisms that thrive in extreme environments on Earth, such as acidic hot springs or deep-sea hydrothermal vents. These resilient life forms expand our understanding of what is biologically possible and challenge us to think beyond Earth-like conditions. As we search the cosmos, we must also consider the implications of finding extraterrestrial life. If we discover microbial life, it would confirm that life is not unique to Earth and might be common throughout the universe. But what if we detect intelligent life? Such a discovery would raise profound questions about communication, coexistence, and the nature of intelligence itself. How would humanity respond to the knowledge that we are not alone? Would it unite us in a shared sense of cosmic connection, or would it spark fear and uncertainty? Conversely, if we find no evidence of life elsewhere, what would that mean for us? The absence of extraterrestrial life would highlight the uniqueness of Earth and the preciousness of its ecosystems. It might also suggest that intelligent life is extraordinarily rare, or that civilizations tend to self-destruct before they can make their presence known. A sobering thought known as the Great Filter Hypothesis. Despite the uncertainties, the search for extraterrestrial life is one of humanity's most profound scientific endeavors. It reflects our innate curiosity and desire to understand our place in the universe. Every new discovery, whether a tantalizing biosignature or a peculiar exoplanet, brings us closer to answering the age-old question: are we alone? As we send probes to icy moons, analyze the atmospheres of distant worlds, and listen for whispers from the stars, we stand on the threshold of a discovery that could redefine existence itself. What lies ahead in this cosmic journey remains unknown, but the possibilities are as vast as the universe itself. Black holes, gateways, or graves of matter. What happens to matter and energy when they are consumed by a black hole? Are black holes the ultimate dead ends of the cosmos? Or could they hold the key to unlocking entirely new realms of physics and even alternate universes? Few phenomena in the universe captivate the imagination like black holes, regions of space-time so warped by gravity that not even light can escape. These cosmic enigmas challenge our understanding of the universe and hint at mysteries far beyond our current scientific grasp. Black holes form from the collapse of massive stars, their cores imploding under the force of gravity when nuclear fusion can no longer sustain them. The result is a singularity, a point of infinite density where space and time cease to exist as we know them. Surrounding this singularity is the event horizon, a boundary beyond which nothing can return. The event horizon is often described as the point of no return, but what truly lies within remains one of the greatest unsolved mysteries in astrophysics. For decades, black holes were theoretical constructs, predicted by Einstein's equations of general relativity. However, mounting observational evidence has turned them into undeniable cosmic realities. The first ever image of a black hole, captured in 2019 by the Event Horizon Telescope, revealed the shadow of a supermassive black hole at the heart of the galaxy M87. This monumental achievement not only confirmed their existence, but also provided a glimpse into the extreme conditions near a black hole's event horizon. But how do black holes influence their surroundings? Far from being mere voids, black holes are dynamic engines of cosmic change. Their immense gravitational pull can trap nearby stars, gas, and dust, creating accretion disks, superheated rings of material spiraling toward the event horizon. As this material accelerates and collides, it emits powerful X-rays and other radiation, making black holes some of the brightest objects in the universe despite their dark cores. Supermassive black holes, millions or even billions of times more massive than the Sun, are found at the centers of most galaxies, including our own Milky Way. These giants play a critical role in galactic evolution, regulating star formation and shaping the motion of stars and gas. Their influence extends far beyond their event horizons, creating jets of particles that can stretch across thousands of light years, sculpting the intergalactic medium. While the mechanics of black holes are awe-inspiring, their deeper mysteries lie in what they might teach us about the nature of the universe itself. One of the most puzzling aspects of black holes is the information paradox. According to quantum mechanics, information about matter cannot be destroyed, yet anything that falls into a black hole seems to vanish forever. This contradiction between quantum mechanics and general relativity has led to intense debate among physicists. Could black holes encode information in their event horizons, as suggested by the holographic principle? Or do they lead to entirely new states of matter and energy? Another tantalizing question is what happens at the singularity. Einstein's equations break down under the extreme conditions inside a black hole, indicating that our current understanding of physics is incomplete. Some theories propose that singularities could be portals to other regions of space-time, or even alternate universes. If this is true, black holes might serve as gateways, not graves, windows into the multiverse or the birthplaces of new universes. Adding to the intrigue, the discovery of primordial black holes offers a glimpse into the earliest moments of the cosmos. These black holes, theorized to have formed shortly after the Big Bang, could account for some of the dark matter in the universe. If detected, they would provide a direct link to the conditions of the early universe and potentially unlock the secrets of cosmic inflation. Even more exotic are concepts like white holes and wormholes, which are theoretical counterparts to black holes. A white hole, the hypothetical reverse of a black hole, would expel matter and energy instead of consuming it, though no evidence for such objects has been found. Wormholes, on the other hand, are speculative structures that could connect distant points in spacetime, offering a theoretical pathway for faster-than-light travel. While these ideas remain highly speculative, they push the boundaries of our understanding and fuel the imagination. In recent years, the study of black holes has been revolutionized by the detection of gravitational waves, ripples in spacetime caused by cataclysmic events like the collision of black holes. The first detection, made by LIGO in 2015, confirmed predictions of Einstein's theory and opened a new era of astronomy. These waves provide a unique way to study black holes, offering insights into their properties, sizes, and the events that create them. Yet, with every discovery, new questions arise. What lies beyond the event horizon? Could black holes harbor exotic forms of matter or energy? And what happens to time and space as they spiral into a singularity? These questions challenge not only our understanding of black holes, but also the very foundations of physics. The possibility of harnessing black holes for energy or exploration has also captured the imagination. Theoretical models suggest that rotating black holes could be used as cosmic energy sources, tapping into the immense rotational energy stored in their spin. Similarly, advanced civilizations might use black holes as gravitational slingshots for interstellar travel, or even as computational devices far beyond our current technological capabilities. For now, black holes remain some of the most mysterious and awe-inspiring objects in the universe. They are not just destroyers but creators, shaping galaxies, igniting the birth of stars, and driving the evolution of the cosmos. As we continue to study these enigmatic phenomena, we inch closer to understanding the universe's deepest mysteries, and perhaps, one day, unlocking the secrets of existence itself. The multiverse theory. Are there infinite realities? Could our universe be just one of countless others, each with its own unique laws, dimensions, and possibilities? The idea of a multiverse, a vast ensemble of parallel universes, might sound like the realm of science fiction, but it has become a serious topic of discussion among physicists and cosmologists. If the multiverse exists, it could profoundly change our understanding of reality, revealing a cosmos far more complex and expansive than we ever imagined. But what is the multiverse theory, and how could it be tested? The multiverse concept arises naturally from several areas of physics. One of the most compelling arguments comes from the theory of cosmic inflation. According to this theory, the universe underwent an unimaginably rapid expansion in the moments after the Big Bang. This inflationary phase not only smoothed out the universe, but may have caused the creation of pocket universes, each with its own physical properties. Our observable universe would be just one of these pockets, separated from countless others by vast, unreachable distances. Another foundation for the multiverse theory comes from quantum mechanics. At the heart of quantum theory is the idea of probabilities. Particles exist in multiple states simultaneously until observed. The many-worlds interpretation of quantum mechanics takes this further, proposing that every quantum decision spawns a new universe. For example, in one universe, you might have chosen coffee over tea this morning, while in another, the opposite occurred. If true, this would mean an infinite number of parallel universes exist, each representing a different outcome of every possible event. String theory, which attempts to unify the forces of nature into a single framework, also supports the multiverse concept. String theory predicts the existence of extra dimensions beyond the familiar three of space and one of time. In some versions, these dimensions could host entire universes with their own physical laws. This brain world idea suggests that our universe might be a three-dimensional slice of a higher dimensional space, with other slices or universes existing alongside us. But what would it mean if the multiverse were real? For one, it would help explain certain fine-tuned aspects of our universe. Physical constants, like the strength of gravity or the charge of an electron, seem precisely calibrated for life to exist. In a multiverse, these constants could vary across different universes. Ours would simply be one where the conditions happen to align to allow life. While this might solve the mystery of fine-tuning, it raises philosophical questions about our significance. Are we special, or just one of countless variations? Testing the multiverse theory, however, is incredibly challenging. By definition, other universes are beyond our observable horizon, making direct detection impossible with current technology. Yet, some researchers propose indirect ways to search for evidence. For example, if our universe collided with another during its early formation, it might leave subtle imprints in the cosmic microwave background radiation. Similarly, gravitational waves, ripples in spacetime, could carry signatures of interactions between universes. The multiverse also invites fascinating questions about its structure. Are all universes part of an infinite continuum, or are they discrete entities? Do they interact? And if so, how? And what forms of matter, energy, or even consciousness might exist in these alternate realities? While these questions remain speculative, they challenge us to expand our thinking beyond the familiar confines of our universe. If the multiverse exists, it could have profound implications for understanding our place in the cosmos. It might reveal that our universe, with all its complexity and beauty, is just one of many, a single chapter in an infinite cosmic library. It also raises ethical and philosophical questions. If alternate versions of ourselves exist in other universes, what does that mean for our identity and free will? Are we merely one possibility among infinite variations? The multiverse theory is not without its critics. Some argue that it ventures into metaphysics rather than science, as it lacks testable predictions. Others worry that the multiverse undermines the search for deeper physical laws by attributing everything to chance. Yet, proponents see the multiverse as a natural extension of our evolving understanding of the cosmos, pushing the boundaries of what science can explore. As we develop more sophisticated tools and theories, we may come closer to answering whether the multiverse is real. Advanced telescopes, like the James Webb Space Telescope, are already probing the edges of the observable universe, and future experiments in particle physics and gravitational waves may uncover hints of other realities. Even if direct evidence remains elusive, the exploration of the multiverse challenges us to think bigger and embrace the unknown. The possibility of infinite realities reshapes how we view our universe and ourselves. Whether or not we ever prove its existence, the multiverse serves as a reminder of the vast potential for discovery in the cosmos. It invites us to ask not only, what is out there, but also, what does it mean to exist? The answers may lie beyond our reach, or they may already be woven into the fabric of reality itself. Quantum entanglement across cosmic distances. Is it possible for two particles, separated by billions of light years, to remain mysteriously connected? Quantum entanglement, often called spooky action at a distance, is one of the most perplexing phenomena in modern physics. It challenges our understanding of space, time, and causality, hinting at a deeper, more interconnected reality underlying the universe. But what exactly is quantum entanglement, and how might it influence the cosmos on the grandest scales? To grasp entanglement, we must first dive into the strange world of quantum mechanics. At the quantum level, particles such as electrons or photons behave in ways that defy classical intuition. They can exist in multiple states simultaneously, known as superposition, until measured. When two particles become entangled, their properties become intrinsically linked, no matter how far apart they are. A change in the state of one particle instantly affects the state of the other, as if they are communicating faster than the speed of light. This apparent instantaneous connection baffled even Albert Einstein, who famously referred to it as spooky action at a distance. He believed that entanglement implied an incomplete understanding of physics and sought a deeper explanation. Yet, experiments repeatedly confirm that entangled particles do behave as quantum mechanics predicts. In fact, the phenomenon is now routinely observed in laboratories, and even used in emerging technologies like quantum cryptography and quantum computing. But what about entanglement on a cosmic scale? Could it play a role in the structure and evolution of the universe itself? Some physicists theorize that quantum entanglement might be fundamental to the very fabric of spacetime. The idea is rooted in the holographic principle, which suggests that the universe can be described by information encoded on its boundaries. If true, entanglement could serve as the threads weaving together the space-time continuum, connecting distant regions of the cosmos in ways we are only beginning to understand. One tantalizing possibility is that entanglement could explain the mysterious phenomenon of dark energy, the force driving the accelerated expansion of the universe. Some models propose that the entanglement of particles across vast distances generates a form of energy inherent to spacetime. While speculative, this idea hints at a profound connection between the quantum world and cosmic-scale phenomena. Entanglement may also shed light on the origins of the universe itself. During the early moments of the Big Bang, all matter and energy were compressed into an unimaginably dense state. In such conditions, particles were likely entangled on an enormous scale. As the universe expanded, these entangled states may have influenced the distribution of matter and energy, shaping the large-scale structures we see today, from galaxies to cosmic filaments. The implications of cosmic entanglement extend beyond physics to questions of philosophy and existence. If entanglement links particles across the universe, it challenges our perception of separateness. Could it be that the cosmos is a single, interconnected entity where all things are fundamentally unified? Such ideas echo ancient philosophical concepts, but now they find resonance in cutting-edge science. Testing entanglement on cosmic scales is a daunting challenge, yet recent experiments offer intriguing possibilities. In one groundbreaking study, researchers used starlight from opposite sides of the sky to determine the randomness of quantum measurements. By selecting photons emitted billions of years ago, the experiment minimized the chance of interference from local factors, providing a glimpse into how entanglement might function across vast cosmic distances. Entanglement could also play a role in the search for extraterrestrial intelligence SETI. Advanced civilizations, if they exist, might use entanglement for communication, bypassing the limitations of light-speed signals. If such quantum beacons exist, detecting them would revolutionize not only SETI, but our understanding of physics and technology. Despite its potential, entanglement remains shrouded in mystery. How do particles know about each other's states instantaneously? Does entanglement defy causality? Or does it reveal a deeper layer of reality beyond space and time? Some physicists suggest that entanglement might involve hidden variables, unknown factors that explain the phenomenon. Others propose that entanglement is a fundamental feature of the universe, requiring no further explanation. What is clear is that entanglement challenges us to rethink the very nature of reality. In the classical view, the universe is composed of distinct, independent objects interacting through forces. Entanglement suggests a different picture, one where connections transcend distance and time, weaving the cosmos into an indivisible whole. If we can unlock its secrets, entanglement might hold the key to unifying quantum mechanics and general relativity, bridging the smallest scales of existence with the largest. As our understanding of entanglement grows, so too does the potential for groundbreaking discoveries. Quantum networks, already in development, could enable secure communication and unprecedented computational power. On a larger scale, entanglement might allow us to probe the universe in ways we never imagined, revealing connections between the quantum and cosmic realms. Ultimately, entanglement is a reminder that the universe is far more interconnected and mysterious than it appears. It invites us to explore not only the nature of particles but the nature of reality itself. Could the entire cosmos be entangled in a vast, unseen web, binding the smallest quanta to the largest galaxies? If so, what does this mean for our understanding of existence and our place within the grand tapestry of the universe? The birth and death of stars, a celestial life cycle. Have you ever considered how stars, those luminous points of light scattered across the night sky, live and die? Stars are not eternal. They are born, evolve, and ultimately perish in spectacular ways, leaving behind remnants that shape the cosmos for billions of years. The story of a star's life is one of transformation, driven by the delicate balance of gravity and nuclear fusion. But how exactly does this cosmic life cycle unfold, and what does it reveal about the universe? The birth of a star begins in the dense, cold regions of space, known as molecular clouds or stellar nurseries. These vast clouds of gas and dust, often spanning light years, are the cradles of star formation. Gravity pulls clumps of material within these clouds together, creating regions of higher density called protostars. As a protostar grows, it heats up, and once its core reaches a critical temperature and pressure, nuclear fusion ignites, marking the birth of a star. Nuclear fusion is the heart of a star's existence, providing the energy that makes it shine. In most stars, hydrogen atoms fuse to form helium, releasing vast amounts of energy in the process. This energy creates outward pressure that counterbalances the inward pull of gravity, stabilizing the star. How long this equilibrium lasts depends on the star's mass. Massive stars burn through their fuel quickly, shining brightly but living short lives, while smaller stars like our Sun burn more slowly, with lifespans stretching billions of years. The mass of a star not only determines its lifespan, but also its eventual fate. Stars like the Sun will eventually exhaust their hydrogen fuel, causing their cores to contract and heat up. This triggers the fusion of helium into heavier elements like carbon and oxygen. At the same time, the outer layers of the star expand, creating a red giant. In the Sun's case, this phase will swell it to many times its current size, possibly engulfing the inner planets, including Earth. For stars like the Sun, the red giant phase ends with the ejection of their outer layers, creating stunning structures called planetary nebulae. What remains is a dense, hot core known as a white dwarf. White dwarfs are incredibly compact, often with the mass of the Sun packed into a volume the size of Earth. Over billions of years, they cool and fade, becoming cold, dark remnants called black dwarfs, though the universe is not yet old enough for any black dwarfs to exist. Massive stars follow a much more dramatic path. These giants can fuse elements all the way up to iron in their cores, but iron cannot undergo fusion to release energy. Once a massive star's core becomes iron-rich, it collapses under its own gravity, triggering a supernova explosion. This cataclysmic event is one of the most energetic in the universe, outshining entire galaxies for a brief time. Supernovae scatter heavy elements like gold, uranium, and calcium into space, seeding the cosmos with the building blocks of planets, and eventually, life. The remnants of a supernova depend on the mass of the original star. If the core is below a certain threshold, it becomes a neutron star, a city-sized object with incredible density. A single teaspoon of neutron star material would weigh billions of tons. Neutron stars often spin rapidly and emit beams of radiation, becoming pulsars that act like cosmic lighthouses. If the star is even more massive, the core collapses into a black hole. These gravitational monsters warp space-time so severely that nothing, not even light, can escape their grasp. Black holes remain some of the most mysterious and fascinating objects in the universe, representing the ultimate fate of matter under extreme conditions. The death of stars is not just an end but a beginning. The elements forged in stars and scattered by supernovae become the raw materials for new stars, planets, and even living organisms. In fact, every atom in your body, from the calcium in your bones to the iron in your blood, was formed in the heart of a star. Carl Sagan famously said, "We are made of star stuff," and this poetic truth underscores our deep connection to the cosmos. The life cycle of stars also drives the evolution of galaxies. Star formation replenishes the light of galaxies, while the death of stars redistributes material and energy. Stellar winds, supernova explosions, and the radiation from massive stars can trigger new waves of star formation, shaping the structure and behavior of galaxies over time. Some regions of space, such as globular clusters, contain stars that have lived for nearly the entire age of the universe. Studying these ancient stars provides valuable insights into the conditions of the early cosmos. By analyzing their compositions and life cycles, astronomers can trace the history of chemical enrichment in the universe, a record written in the light of stars. Advancements in technology have allowed scientists to study stars at every stage of their lives. Observatories like the Hubble Space Telescope and the James Webb Space Telescope have captured breathtaking images of stellar nurseries, planetary nebulae, and supernova remnants. These observations reveal the intricate processes that govern star formation and death, offering glimpses into the universe's ongoing story of creation and destruction. Despite our growing understanding, many mysteries about stars remain. What triggers the collapse of a molecular cloud into a protostar? How do stars with masses hundreds of times greater than the Sun form and evolve? And what role do magnetic fields play in shaping stellar activity and evolution? These questions continue to drive research, pushing the boundaries of astrophysics. The birth and death of stars remind us of the impermanence of even the most seemingly eternal objects in the universe. They are a testament to the cycles of creation and destruction that define existence, both on cosmic scales and in our own lives. As we study these celestial phenomena, we not only learn about the universe but also about ourselves, our origins, our place in the cosmos, and the shared journey of all matter through time and space. Gravitational waves, messages from the universe's past. What if we could listen to the universe, capturing the echoes of cataclysmic events from billions of years ago? Gravitational waves, ripples in space-time caused by the movement of massive objects, offer precisely this opportunity. First predicted by Albert Einstein over a century ago as part of his theory of general relativity, gravitational waves were considered nearly impossible to detect until 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, captured the faint whisper of two colliding black holes. This groundbreaking discovery marked the beginning of a new era in astronomy, enabling scientists to observe the universe in an entirely new way. But what are gravitational waves, and what secrets do they hold? Gravitational waves are distortions in the fabric of space-time itself, created by accelerating masses. Imagine tossing a stone into a still pond and watching the ripples spread outward. Gravitational waves behave similarly, but they ripple through space-time rather than water. These waves propagate at the speed of light, carrying information about the events that generated them. The most powerful gravitational waves are produced by extreme cosmic events, such as the collision of black holes, merging neutron stars, or the violent explosions of supernovae. The detection of gravitational waves is a technological marvel. LIGO and its European counterpart, Virgo, use enormous laser-based instruments called interferometers to measure the infinitesimal distortions caused by passing waves. These distortions are incredibly small, thousands of times smaller than the diameter of a proton, but advanced technology allows scientists to detect them with remarkable precision. In 2015, LIGO observed the first gravitational wave signal, GW150914, which originated from the merger of two black holes over 1 billion light-years away. Gravitational waves provide a new way of studying the universe, complementing traditional methods that rely on electromagnetic radiation, such as light, X-rays, or radio waves. Unlike light, gravitational waves are unaffected by matter, allowing them to travel unimpeded through the densest regions of space. This means they carry unaltered information about the most violent and inaccessible phenomena in the universe. By listening to gravitational waves, scientists can uncover details about black holes, neutron stars, and even the earliest moments of the universe. One of the most remarkable discoveries enabled by gravitational waves was the 2017 detection of GW170817, a signal from the merger of two neutron stars. This event, observed both through gravitational waves and electromagnetic signals, provided unprecedented insights into the production of heavy elements like gold and platinum. It also confirmed that neutron star mergers are the source of short gamma-ray bursts, some of the most energetic explosions in the cosmos. This marked the dawn of multi-messenger astronomy, where gravitational waves and light are used together to study the universe. Gravitational waves also have the potential to reveal hidden aspects of black holes. For instance, by analyzing the signals from black hole mergers, scientists can measure their masses and spins with incredible accuracy. These observations have already challenged theories about how black holes form, revealing unexpected properties and behaviors. Could there be different types of black holes we have yet to discover? Or are there phenomena we don't yet understand influencing their mergers? The study of gravitational waves extends even further, offering glimpses into the early universe. Shortly after the Big Bang, the universe was a dense, opaque plasma, making it impossible for light to escape. However, gravitational waves could travel freely, carrying information from this primordial epoch. If we can detect these primordial gravitational waves, they could reveal details about cosmic inflation, the rapid expansion of the universe in its first fractions of a second. Such discoveries would provide a direct link to the birth of the cosmos and offer clues about the fundamental forces shaping reality. The search for gravitational waves continues to advance. New detectors, such as the Japanese KAGRA and the upcoming LISA, Laser Interferometer Space Antenna, aim to expand our observational capabilities. LISA, in particular, will operate in space, allowing it to detect gravitational waves from sources inaccessible to ground-based observatories, such as supermassive black hole mergers and other low-frequency events. These developments promise to unveil a broader spectrum of gravitational wave phenomena, deepening our understanding of the universe. Gravitational waves also challenge our theoretical frameworks, pushing the boundaries of general relativity. By comparing observed waveforms with predictions from Einstein's equations, scientists can test the limits of the theory under extreme conditions. So far, general relativity has held up remarkably well, but future observations could reveal deviations that hint at new physics, such as quantum gravity or extra dimensions. The implications of gravitational waves extend beyond astrophysics to fundamental questions about the nature of spacetime. Are these waves truly distortions of spacetime, or could they hint at something even deeper, such as a hidden layer of reality? Some theorists suggest that gravitational waves could interact with dark matter or dark energy, potentially offering insights into these elusive components of the universe. The discovery of gravitational waves has also captured the public's imagination, inspiring awe and wonder about our connection to the cosmos. These ripples remind us that the universe is not static but dynamic, constantly evolving through cycles of creation and destruction. They are a testament to human ingenuity, revealing how far we've come in our quest to understand the universe. As we continue to detect and study gravitational waves, we are not just learning about the cosmos, we are expanding the very way we perceive reality. Each wave carries a message from the distant past, a whisper from events that shaped the universe long before Earth existed. By listening to these messages, we gain a deeper appreciation for the interconnectedness of space, time, and matter, and our place in the vast cosmic story. Time travel, fact or fiction in the laws of physics. Could time travel ever become more than the stuff of science fiction? From blockbuster films to classic literature, the idea of journeying through time has captivated human imagination for centuries. But how does this concept hold up under the scrutiny of physics? Is time travel theoretically possible within the framework of the universe's laws? Or is it destined to remain an unattainable dream? To explore this, we must delve into the nature of time itself and the strange, sometimes paradoxical possibilities suggested by modern science. Time, as we experience it, seems linear, an unyielding march from past to present to future. But Einstein's theory of relativity revolutionized our understanding of time, showing that it is not an absolute, standalone entity, but rather intertwined with space in a four-dimensional fabric called spacetime. This union of space and time is dynamic, bending and stretching under the influence of gravity and motion. These principles lay the groundwork for the theoretical possibility of time travel. One of the most straightforward forms of time travel, according to relativity, is traveling to the future. This can be achieved through time dilation, a phenomenon where time flows differently for observers in different conditions. For instance, an astronaut traveling near the speed of light would experience time much more slowly than someone on Earth. Upon returning, the astronaut would find that far more time had passed on Earth than for them, a journey into the future. This effect, though slight, has been confirmed experimentally with atomic clocks placed on high-speed aircraft and satellites. But what about traveling to the past? This is where the concept becomes far more contentious and complicated. One theoretical pathway involves wormholes, hypothetical tunnels in spacetime that connect distant points. If one end of a wormhole were accelerated to near light speed and then brought back to its original position, a time difference would exist between the two ends. In theory, stepping into one end could allow a traveler to emerge at an earlier point in time. However, this idea faces significant challenges, not least of which is the immense energy required to create and stabilize a wormhole. Another proposal for backward time travel involves closed time-like curves, solutions to Einstein's equations that describe paths through spacetime that loop back on themselves. These curves could theoretically allow an object or person to travel back to their own past. However, closed time-like curves raise profound paradoxes, such as the grandfather paradox, where altering events in the past could prevent the time traveler's existence, creating a logical inconsistency. Physicists have devised ways to address these paradoxes, including the Novikov's self-consistency principle. This principle suggests that any action taken by a time traveler in the past would be consistent with the history that already exists, effectively preventing paradoxes. For example, even if someone tried to prevent their grandparents from meeting, events would conspire to ensure their actions ultimately led to the same outcome. While intriguing, this idea remains purely speculative. Quantum mechanics, with its inherent unpredictability and probabilistic nature, adds another layer of complexity to time travel. Some theories suggest that quantum phenomena could allow for time loops or alternate timelines. In the many-worlds interpretation of quantum mechanics, traveling to the past might create a branching timeline, where the traveler's actions result in a parallel universe rather than altering their original history. If true, this would sidestep paradoxes by allowing multiple realities to coexist. Despite these theoretical possibilities, significant hurdles remain. One major issue is the energy required for time travel. The creation of a stable wormhole or closed time-like curve would likely require exotic matter with negative energy density, a form of matter that has not yet been observed in nature. Additionally, the extreme conditions near wormholes or other space-time distortions could destroy any traveler attempting to pass through. Another challenge is the question of causality, the principle that cause precedes effect. Time travel to the past could violate causality, potentially unraveling the logical order of events in the universe. Some physicists argue that such violations are fundamentally prohibited, making backward time travel impossible. Others suggest that quantum effects or as yet undiscovered physical laws might resolve these issues, keeping causality intact. While the practical realization of time travel remains far out of reach, its study has profound implications for our understanding of the universe. It forces us to grapple with the nature of time, the structure of space-time, and the limits of human knowledge. Time travel also intersects with philosophical questions about free will, determinism, and the nature of reality. If time travel were possible, would the future be fixed, or could we alter it? And what would it mean to step outside the flow of time, experiencing it as a dimension rather than a sequence? In popular culture, time travel often serves as a metaphor for regret, hope, or the longing to change the past. In science, however, it represents the ultimate challenge to our understanding of the cosmos. It pushes the boundaries of physics and imagination, offering a tantalizing glimpse of what might be possible in the far future. For now, time travel remains theoretical, constrained by the limits of our technology and understanding. Yet, the very act of contemplating it expands our horizons, reminding us that the universe is filled with mysteries waiting to be unraveled. Whether or not time travel becomes a reality, the journey to explore its possibilities is a testament to human curiosity and the drive to transcend the boundaries of what we know. The Big Bang, unraveling the universe's fiery beginning. What truly happened at the moment the universe was born? The Big Bang is more than a theory. It is the cornerstone of modern cosmology, a framework that explains the origins of the cosmos and its evolution over billions of years. But while the concept is widely accepted, the Big Bang raises profound questions about the nature of time, space, and existence itself. What caused it? What came before? And how does it continue to shape the universe today? The term Big Bang often conjures the image of a colossal explosion, but this description is misleading. The Big Bang was not an explosion in space. It was the rapid expansion of space itself. Approximately 13.8 billion years ago, the universe began as an unimaginably hot, dense singularity, a point where all matter, energy, and the very fabric of spacetime were concentrated. In the first fractions of a second, this singularity expanded and cooled, setting the stage for the formation of everything we observe today. One of the most compelling pieces of evidence for the Big Bang is the cosmic microwave background, CMB, a faint glow of radiation that permeates the universe. Discovered in 1965, the CMB is a relic from when the universe was just 380,000 years old, a time when it had cooled enough for light to travel freely. This ancient radiation serves as a snapshot of the early cosmos, confirming that the universe was once a hot, dense plasma before evolving into its current state. Another key line of evidence is the observation that galaxies are moving away from us, with more distant ones receding faster. This phenomenon, known as the Hubble-Lemaitre law, indicates that the universe is expanding. By extrapolating this expansion backward, scientists concluded that the universe must have originated from a single, compact point. The discovery of this expansion revolutionized our understanding of the cosmos, demonstrating that the universe is dynamic, not static. But how did the Big Bang unfold in its earliest moments? The theory of cosmic inflation offers a fascinating glimpse into the universe's infancy. Inflation proposes that a fraction of a second after the Big Bang, the universe underwent a brief but exponential expansion, growing from subatomic scales to macroscopic size almost instantaneously. This rapid inflation smoothed out irregularities, explaining why the universe appears so uniform on large scales while still containing the small fluctuations that seeded the formation of galaxies. During the first moments after inflation, the universe was a seething soup of fundamental particles, quarks, gluons, and photons, moving at near-light speeds. As it cooled, these particles combined to form protons and neutrons, laying the foundation for atomic nuclei. This process, called nucleosynthesis, occurred within the first 3 minutes and produced the lightest elements: hydrogen, helium, and trace amounts of lithium. Heavier elements would not form until much later, within the cores of stars. Yet, the Big Bang leaves us with some profound mysteries. For instance, what caused the singularity to expand in the first place? While inflation explains much about the universe's early moments, it does not address the ultimate origin of the singularity or the mechanisms behind its rapid expansion. Some theories propose that the Big Bang was a transition from a previous state, such as a collapsing universe or a quantum fluctuation in a primordial void. Others suggest it might be one of many Big Bangs in a multiverse, where countless universes are born and evolve independently. Another unresolved question is what came before the Big Bang. Traditional physics suggests that time itself began with the Big Bang, making the question meaningless in a classical sense. However, quantum gravity theories, such as string theory and loop quantum gravity, suggest that space-time might have a more complex structure, allowing for phenomena before the Big Bang. These ideas remain speculative, but challenge our understanding of time as a linear, unidirectional flow. The Big Bang also raises questions about the fate of the universe. If the cosmos began in a fiery expansion, how will it end? The answer depends on the interplay between gravity, dark energy, and the overall density of matter. If gravity dominates, the universe could reverse its expansion and collapse in a big crunch. Alternatively, if dark energy continues to accelerate expansion, the universe might drift into a big freeze, where galaxies move so far apart that stars die out, leaving a cold, dark cosmos. A third possibility, the Big Rip, envisions dark energy tearing apart galaxies, stars, and even atoms as the expansion accelerates uncontrollably. Despite its successes, the Big Bang theory is not without challenges. One puzzling aspect is the nature of dark matter and dark energy, which together constitute about 95% of the universe's mass energy content, but remain largely unexplained. Dark matter, inferred from its gravitational effects, and dark energy, the force driving cosmic acceleration, are essential to our understanding of the universe, yet defy direct detection. How these components fit into the Big Bang framework is one of the most pressing questions in modern cosmology. The Big Bang also inspires profound philosophical and existential questions. If the universe had a beginning, does it have a purpose or a creator? While science seeks natural explanations, the concept of a finite, evolving cosmos challenges our understanding of existence and our place within it. The very fact that we can trace the universe's origin speaks to the power of human curiosity and our ability to unravel the mysteries of the cosmos. As scientists probe deeper into the Big Bang, they employ ever more advanced tools and techniques. Observatories like the James Webb Space Telescope aim to peer further back in time, capturing light from the universe's first stars and galaxies. Particle accelerators, such as the Large Hadron Collider, recreate conditions similar to those moments after the Big Bang, providing insights into the fundamental forces and particles that govern the universe. While we may never fully answer every question about the Big Bang, its study reveals the interconnectedness of all things. From the tiniest particles to the grandest galaxies, the universe's story is one of evolution, transformation, and endless possibility. As we continue to explore this cosmic beginning, we are reminded of the boundless curiosity that drives us to understand the universe and ourselves. Cosmic voids. What do they tell us about dark matter? Have you ever wondered what lies in the vast, empty spaces between galaxies? These seemingly barren regions, known as cosmic voids, are among the largest structures in the universe, spanning hundreds of millions of light years. At first glance, voids appear to be devoid of matter, but their role in the cosmos is anything but empty. They hold critical clues about the distribution of matter, the nature of dark energy and dark matter, and the large-scale structure of the universe. But what are cosmic voids, and what can they teach us about the hidden forces shaping the cosmos? Cosmic voids are immense regions of space with a strikingly low density of galaxies, stars, and matter compared to the cosmic average. They form a key component of the large-scale structure of the universe, often referred to as the cosmic web. This web is composed of filaments of galaxies and dark matter, which intersect at dense nodes, creating clusters of galaxies. Between these filaments lie the voids, vast undepopulated regions that make up about 80% of the universe's volume, but contain only 10% of its mass. The existence of cosmic voids arises from the gravitational dynamics of the early universe. Shortly after the Big Bang, slight density fluctuations in the cosmic microwave background caused matter to clump together in some regions while leaving others sparse. Over billions of years, gravity amplified these differences, pulling matter into dense filaments and leaving behind the empty voids we see today. The distribution of these voids provides a map of the universe's evolution, offering insights into how matter has moved and clustered over time. Cosmic voids are not entirely empty. They contain small amounts of gas, dark matter, and a few isolated galaxies. However, their low density makes them ideal laboratories for studying dark energy and dark matter. Because voids lack the gravitational pull of dense regions like galaxy clusters, their expansion is more directly influenced by dark energy, the mysterious force driving the accelerated expansion of the universe. By analyzing how voids grow over time, scientists can test theories about dark energy's behavior and properties. Dark matter, too, leaves its imprint on cosmic voids. Though invisible, dark matter dominates the mass of the universe and exerts a gravitational influence that shapes the distribution of galaxies and voids. Simulations of the cosmic web, which incorporate both ordinary and dark matter, predict the size, shape, and evolution of voids. Comparing these models to observations helps refine our understanding of dark matter and its role in the universe. One intriguing feature of voids is their ability to act as natural magnifying lenses for detecting subtle cosmic effects. For instance, the light from distant galaxies passing through a void is slightly distorted due to gravitational lensing, a bending of spacetime caused by the presence of matter. By studying these distortions, astronomers can map the distribution of dark matter within voids, revealing its otherwise hidden presence. Cosmic voids also play a role in testing the foundations of cosmology. Their large size and isolation make them sensitive to deviations from standard physics, such as alternative theories of gravity. If gravity behaves differently in voids compared to dense regions, it could point to new physics beyond Einstein's general relativity. Such discoveries could revolutionize our understanding of space-time and the forces that govern the universe. Another fascinating aspect of voids is their impact on galaxies within and around them. Galaxies inside voids often appear different from their counterparts in denser regions. They tend to have lower star formation rates, less dense interstellar gas, and distinct morphologies. These differences suggest that a galaxy's environment plays a significant role in its evolution. Studying void galaxies offers clues about how isolation influences star formation, black hole activity, and the chemical enrichment of the cosmos. Despite their apparent emptiness, voids may also host exotic phenomena. Some theories propose that voids could amplify the effects of cosmic inflation, leaving subtle imprints in their structure. Others suggest that voids might enhance the detection of neutrinos, elusive, nearly massless particles that rarely interact with matter. If confirmed, these effects would provide valuable tools for probing the early universe and the fundamental particles that shape it. The study of cosmic voids has advanced rapidly in recent years, thanks to increasingly powerful surveys and simulations. Projects like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, have mapped millions of galaxies, allowing scientists to identify and analyze thousands of voids. Meanwhile, supercomputer simulations recreate the formation of the cosmic web, providing a virtual laboratory for testing hypotheses about voids and their properties. One of the most ambitious upcoming projects is the Euclid mission, a space telescope designed to study the geometry of the universe and the effects of dark energy. Euclid's precise measurements of galaxy clustering and void distribution will provide unparalleled insights into the structure and evolution of the cosmic web. Similarly, the Rubin Observatory will map the positions of billions of galaxies, enabling a more detailed understanding of voids than ever before. As our knowledge of cosmic voids grows, so too does our appreciation for their role in the universe. These vast regions, once dismissed as mere empty spaces, are now recognized as critical components of the cosmic puzzle. They reveal the interplay between gravity, dark matter, and dark energy, shedding light on the forces that have shaped the universe over billions of years. Perhaps the most profound lesson of cosmic voids is their reminder of the universe's balance. For every dense cluster of galaxies, there is an opposing void, a yin and yang of structure and emptiness. This interplay mirrors the dualities found throughout nature, from light and shadow to creation and destruction. In studying voids, we not only uncover the secrets of the cosmos, but also deepen our understanding of the profound harmony underlying existence. The enigma of fast radio bursts. What could cause a burst of energy so powerful that it outshines entire galaxies, yet lasts only milliseconds? Fast radio bursts, FRBs, are one of the most puzzling phenomena in modern astronomy. Discovered in 2007, these mysterious flashes of radio waves originate from far beyond our galaxy, and despite years of study, their origins remain elusive. Are they the signatures of extreme cosmic events, the activities of magnetars or other exotic astrophysical objects, or could they even be signs of advanced alien civilizations? FRBs are exceptionally brief bursts of radio waves, each lasting just a few milliseconds. Yet during this fleeting time, they emit as much energy as the sun does in a day. They were first detected by chance, buried in archival data from a radio telescope. Since then, hundreds of FRBs have been discovered, yet their sources remain shrouded in mystery. Unlike pulsars, which emit predictable and periodic signals, most FRBs appear as one-off events, adding to the challenge of studying them. The first major breakthrough came in 2016 with the discovery of a repeating FRB, known as FRB 121102. Unlike most FRBs, this one emitted multiple bursts over time, allowing astronomers to pinpoint its origin, a dwarf galaxy over 3 billion light-years away. This discovery suggested that at least some FRBs might come from persistent sources, such as highly magnetized neutron stars called magnetars. Magnetars, with their intense magnetic fields, are capable of releasing enormous amounts of energy in sudden bursts, aligning well with the observed characteristics of FRBs. But not all FRBs fit neatly into this explanation. Some bursts are far more energetic than magnetars are typically thought to produce. Others seem to follow strange patterns, such as FRB 180916, which repeats every 16 days, suggesting a possible connection to binary star systems or even the rotation of massive objects. These variations hint that FRBs might not come from a single type of source, but rather from a diverse range of astrophysical phenomena. Adding to the intrigue, the distribution of FRBs across the sky shows no preference for our galaxy, indicating that they are truly extragalactic in origin. Their incredible distances, combined with their brief durations, make them challenging to study. However, their travels through intergalactic space offer unique opportunities for exploration. As FRBs pass through clouds of gas and plasma, they become dispersed, with longer wavelengths arriving slightly later than shorter ones. By analyzing this dispersion, astronomers can learn about the density and composition of the matter between galaxies, a method that has already provided insights into the elusive, missing baryons of the universe. One of the most controversial questions surrounding FRBs is whether they could be signals from intelligent extraterrestrial civilizations. The immense energy and regularity of some bursts have fueled speculation that they might be artificial, perhaps created by advanced technologies as beacons or propulsion systems. For instance, one hypothesis suggests that FRBs could be the leakage from energy beams used to power interstellar spacecraft. While there is no concrete evidence to support this idea, the mere possibility has captured the public's imagination and spurred further research. In recent years, technological advancements have accelerated the hunt for FRBs. Radio telescopes like CHIME, Canadian Hydrogen Intensity Mapping Experiment, and ESCAP, Australian Square Kilometre Array Pathfinder, have dramatically increased the detection rate, identifying hundreds of new bursts. These instruments are equipped to scan large portions of the sky continuously, catching FRBs in real time and enabling rapid follow-up observations. These efforts have revealed surprising trends, such as the fact that some FRBs appear clustered in specific regions, suggesting an association with particular types of galaxies or cosmic environments. Despite these advances, many questions remain. For instance, why do some FRBs repeat while others do not? Are repeating and non-repeating FRBs fundamentally different phenomena, or are we simply observing different stages of the same process? Moreover, what is the true role of magnetars, black holes, and other extreme objects in producing these bursts? The answers to these questions may hold the key to understanding not just FRBs, but also the extreme physics of the universe. FRBs have also proven valuable as cosmic tools. By acting as natural probes of the intergalactic medium, they help scientists study the large-scale structure of the universe. Their dispersive signals provide data on the amount and distribution of matter in space, filling gaps in our understanding of the cosmos. Additionally, some researchers are exploring the use of FRBs as cosmic clocks, leveraging their regularity to test fundamental constants of nature and the behavior of spacetime. The future of FRB research is bright, with new telescopes and collaborations poised to unlock their secrets. The Square Kilometre Array, SK, set to become the world's largest radio telescope, promises unprecedented sensitivity and resolution, potentially identifying thousands of FRBs per year. Meanwhile, dedicated instruments like the Deep Synoptic Array aim to localize FRB sources with pinpoint accuracy, revealing the environments from which they emerge. The enigma of FRBs represents the cutting edge of astrophysics, blending the study of extreme cosmic events with questions about the nature of the universe itself. As we continue to unravel their mysteries, we may not only solve the puzzle of these fleeting bursts, but also uncover new phenomena and principles that reshape our understanding of the cosmos. Could FRBs be the first whispers of an entirely new kind of astrophysics, or even a clue to our place in the universe? The answers may lie in the next burst, waiting to be detected and decoded. How do planets form? A look at the stellar cradle. How does the chaotic process of star formation give rise to planets like Earth? The creation of planets is one of the most fascinating and intricate phenomena in the universe, transforming swirling clouds of gas and dust into the diverse worlds we observe today. This cosmic alchemy, known as planetary formation, offers insights into not only our solar system's origins, but also the potential for life elsewhere in the universe. But how exactly do planets form, and what conditions are necessary to produce such a remarkable variety of worlds? Planet formation begins in the aftermath of a star's birth. When a molecular cloud collapses under gravity, it forms a dense, rotating disk of gas and dust surrounding the young star. This disk, called a protoplanetary disk, serves as the nursery for planets. Observations from telescopes like ALMA, Atacama Large Millimeter/Submillimeter Array, have provided breathtaking images of these disks, revealing intricate patterns of rings and gaps where planets may already be forming. The process starts with the smallest building blocks, microscopic particles of dust. In the disk, these grains collide and stick together through electrostatic forces, forming larger clumps called planetesimals. Over time, planetesimals grow into larger bodies through a process called accretion, where gravity becomes the dominant force. These growing bodies, now hundreds of kilometers across, become the seeds of planets. But the journey from planetesimal to fully formed planet is far from smooth. Collisions between growing bodies can be both constructive and destructive, with some merging to form larger objects while others are shattered into debris. This chaotic phase, known as the runaway growth stage, sees the rapid accumulation of mass as the largest bodies dominate their surroundings, sweeping up material. As planets grow, their ability to influence their environment increases. Massive planets can carve gaps in the protoplanetary disk, redirecting gas and dust and shaping the structure of the disk itself. These interactions explain the striking features observed in many young star systems, where bright rings and dark gaps hint at the presence of emerging planets. The type of planet that forms depends largely on its distance from the star and the composition of the disk. Close to the star, where temperatures are higher, only rocky materials can condense, giving rise to terrestrial planets like Earth, Venus, and Mars. Farther out, beyond the frost line, temperatures drop low enough for volatile compounds like water, methane, and ammonia to freeze, forming icy cores. These cores can grow large enough to capture massive envelopes of gas, creating gas giants like Jupiter and Saturn. Beyond gas giants, even more exotic planets can form. In some cases, icy cores that fail to accumulate significant gas become ice giants, like Uranus and Neptune. Meanwhile, planets forming in dense, metal-rich regions may become super-Earths or mini-Neptunes, planets larger than Earth but smaller than Neptune, a type of world not found in our solar system but common among exoplanets. The diversity of planetary systems observed today reflects the dynamic and often chaotic nature of planet formation. Some systems, like our own, exhibit well-ordered orbits, while others contain planets with highly eccentric paths, likely the result of gravitational interactions or past collisions. Observations of hot Jupiters, gas giants orbiting perilously close to their stars, have revealed that planetary migration plays a key role in shaping systems. These migrations occur when young planets interact with the disk or other planets, causing them to spiral inward or outward from their original positions. Another intriguing aspect of planet formation is the role of moons and rings. In many cases, moons form from the debris left over after collisions or from material captured by a planet's gravity. Saturn's iconic rings, for instance, are thought to be the remnants of a shattered moon or icy planetesimals that failed to coalesce. Understanding these processes provides clues about the history of our own moon, which likely formed after a massive collision between Earth and a Mars-sized body early in the solar system's history. The discovery of thousands of exoplanets has expanded our understanding of planetary formation beyond the solar system. Observations reveal that planetary systems are incredibly diverse, ranging from tightly packed systems of small, rocky planets to massive gas giants orbiting at vast distances. These discoveries challenge traditional models of planet formation, forcing scientists to revise their theories to account for such variety. Key to these advancements are technologies like the James Webb Space Telescope, which can observe the atmospheres of young planets still embedded in their protoplanetary disks. By analyzing the composition of these atmospheres, scientists can infer the conditions under which these planets formed, shedding light on the complex interplay between gas, dust, and gravity. One of the most profound questions in planetary science is how often the process of planet formation leads to conditions suitable for life. Earth is a testament to the delicate balance required to sustain life. The right distance from the sun, a stable climate, and the presence of water and other essential elements. Studying planet formation helps scientists identify these Goldilocks conditions elsewhere, guiding the search for potentially habitable worlds. Yet, many mysteries remain. For instance, why does our solar system lack super-Earths, which are common in other systems? What role do magnetic fields play in shaping protoplanetary disks and influencing planet formation? And how does the chaotic process of planet formation create systems as stable as our own? The answers to these questions lie in the continued study of planetary systems, both within and beyond our solar neighborhood. By piecing together the story of how planets form, astronomers hope to not only understand our cosmic origins, but also uncover the potential for life in the universe. Planet formation is more than just a process. It is the foundation of the cosmos as we know it. Each step, from the coalescence of dust grains to the emergence of diverse worlds, is a testament to the creativity and complexity of the universe. As we uncover the secrets of this process, we draw closer to answering one of humanity's oldest questions. How do we come to be? The mystery of rogue planets wandering in the dark. What happens when a planet loses its tether to a star and drifts through the cosmos alone? Rogue planets, also known as free-floating or nomadic planets, are among the most enigmatic objects in the universe. Unlike the planets in our solar system, which orbit the sun in predictable paths, rogue planets wander through interstellar space without the gravitational anchor of a star. Their origins, characteristics, and potential for hosting life are subjects of intense scientific intrigue. But how do these celestial nomads form, and what secrets might they hold about the universe? The existence of rogue planets was first theorized decades ago, but their discovery has proven exceedingly difficult. Without the light of a host star to illuminate them, rogue planets are nearly invisible against the darkness of space. However, advanced detection methods, such as gravitational microlensing, have confirmed their presence. This technique relies on the bending of light caused by a planet's gravitational field as it passes in front of a distant star, briefly magnifying the star's light. Such observations have revealed that rogue planets are likely abundant, with estimates suggesting there could be billions in our galaxy alone. But where do rogue planets come from? One possibility is that they are ejected from their original planetary systems. During the chaotic early stages of a planetary system's formation, gravitational interactions between young planets and their neighbors can send some worlds hurtling into interstellar space. These interactions may be especially common in densely packed systems or those with massive planets, where the gravitational forces are strong enough to destabilize orbits. Another potential origin is direct formation in interstellar space. In this scenario, rogue planets form in isolation from collapsing clouds of gas and dust, similar to stars but on a smaller scale. This process would produce planets with characteristics distinct from those formed in traditional planetary systems, potentially lacking the layered compositions typical of planets that form in protoplanetary disks. The environments of rogue planets are extreme and varied. Without the warmth of a star, most rogue planets are incredibly cold, with temperatures plunging to near absolute zero. However, some rogue planets may retain internal heat generated during their formation or through radioactive decay in their cores. This residual heat could create subsurface oceans beneath thick layers of ice, offering a potential habitat for life. The discovery of subsurface oceans on moons like Europa and Enceladus suggests that such environments could harbor microbial life, even in the absence of sunlight. Moreover, rogue planets with thick atmospheres might trap heat effectively, maintaining temperatures suitable for liquid water. These atmospheres could be composed of hydrogen or other greenhouse gases, creating a kind of blanket that preserves warmth. If such conditions exist, rogue planets might represent unexpected oases of habitability in the otherwise desolate void of interstellar space. One of the most tantalizing possibilities is that rogue planets could serve as natural arcs, carrying the ingredients for life across the galaxy. As these planets drift through interstellar space, they may pass through molecular clouds or encounter other planetary systems, exchanging material and potentially seeding life in new environments. This idea, known as panspermia, posits that life or its building blocks could spread throughout the cosmos via wandering planets and other celestial bodies. Despite their isolation, rogue planets could interact with the galactic environment in fascinating ways. As they move through the galaxy, they may encounter dense regions of interstellar gas, gravitationally capturing material that alters their compositions. These interactions could provide clues about the chemical makeup of the regions they traverse, offering insights into the broader structure of the galaxy. Detecting and studying rogue planets remains one of the greatest challenges in modern astronomy. Gravitational microlensing has proven effective for identifying these elusive objects, but it provides only brief glimpses of their existence. Future missions, such as the Nancy Grace Roman Space Telescope, aim to expand our ability to detect rogue planets and study their properties in greater detail. Advanced infrared observatories may also help, as rogue planets emit faint heat signatures that could reveal their sizes, compositions, and atmospheric conditions. The potential for finding life on rogue planets is an exciting frontier. While they lack the energy input from a star, the possibility of subsurface oceans and geothermal activity provides a tantalizing hint that life could persist in these dark worlds. Exploring this idea requires innovative approaches, including the development of sensitive instruments capable of detecting biosignatures in the faint emissions of rogue planets. The study of rogue planets also challenges traditional notions of what makes a world habitable. Earth's reliance on sunlight has shaped our understanding of life, but rogue planets demonstrate that other energy sources, such as geothermal heat, could sustain ecosystems. This expands the definition of habitability and highlights the resilience of life in extreme environments. Rogue planets also prompt profound philosophical questions. What does it mean for a world to exist in isolation, disconnected from the gravitational embrace of a star? Could such planets harbor civilizations? And if so, how might they perceive the universe without the guiding light of a sun? These questions underscore the diversity of planetary systems and the potential for life to adapt to conditions far different from those on Earth. As we continue to explore the universe, rogue planets remind us of the boundless creativity of cosmic processes. They are testaments to the dynamic and often chaotic nature of planetary systems, offering glimpses of worlds that defy conventional expectations. Each rogue planet is a story waiting to be uncovered, a chapter in the vast and ever-evolving narrative of the cosmos. What other secrets might these wandering worlds reveal? The answers may lie in the faint glimmers of light they reflect or the subtle distortions they create as they traverse the galaxy. With each discovery, we come closer to understanding not just rogue planets but the nature of the universe itself. The strange world of exoplanets. Could we ever live there? Could humanity one day call another planet home? As our understanding of exoplanets, planets orbiting stars beyond our solar system, expands, this question becomes ever more pressing. With over 5,000 confirmed exoplanets and counting, the universe appears teeming with worlds, some eerily similar to Earth and others unlike anything in our solar system. What do these distant worlds teach us about habitability, and could one of them become humanity's future refuge? The search for exoplanets began in earnest in the 1990s, and since then, it has reshaped our understanding of planetary systems. The first confirmed exoplanet, 51 Pegasi b, was a hot Jupiter, a gas giant orbiting perilously close to its star. This discovery shattered expectations based on our solar system, revealing that planetary systems can take forms far different from our own. Subsequent observations have uncovered a dazzling variety of planets, from rocky super-Earths to icy mini-Neptunes, and even rogue planets drifting through interstellar space. One of the key goals in exoplanet research is identifying potentially habitable worlds. These planets must meet several criteria, chief among them being their location in the habitable zone, the region around a star where temperatures allow for liquid water to exist. However, being in the habitable zone is just the beginning. A planet's atmosphere, composition, and magnetic field also play critical roles in its ability to support life. Earth-like planets, with rocky surfaces and atmospheres capable of sustaining liquid water, are prime candidates for habitability. Planets like Proxima Centauri b, orbiting the nearest star to our solar system, have sparked intense interest due to their potential Earth-like qualities. However, Proxima Centauri b lies close to a red dwarf star, which emits intense flares that could strip away its atmosphere, challenging its habitability. The diversity of exoplanets has forced scientists to rethink what makes a planet suitable for life. For instance, super-Earths, planets larger than Earth but smaller than Neptune, are among the most common types of planets detected. Their larger size could allow for thicker atmospheres, which might protect against stellar radiation and maintain stable climates. Similarly, some ice giants might host subsurface oceans beneath thick layers of ice, creating environments analogous to the icy moons of our solar system, like Europa and Enceladus. The atmospheres of exoplanets are crucial in determining their habitability. By analyzing the light passing through or reflected by a planet's atmosphere, scientists can identify its chemical composition. Molecules like oxygen, methane, and water vapor could indicate the presence of biological processes. Instruments like the James Webb Space Telescope are designed to study these atmospheres in unprecedented detail, bringing us closer to identifying potentially life-supporting worlds. However, living on an exoplanet poses challenges far beyond finding one with the right conditions. Most exoplanets are light years away, making travel to them a monumental task. Even Proxima Centauri b, the nearest potentially habitable exoplanet, is over 4 light-years away, a distance that would take thousands of years to traverse with current technology. Advancements in propulsion systems, such as nuclear fusion or light sails, will be critical if humanity ever hopes to reach these distant worlds. Even if we could reach an exoplanet, adapting to its conditions would be another hurdle. Differences in gravity, atmospheric composition, and radiation levels could make long-term survival difficult. For instance, a planet with stronger gravity than Earth would require significant adaptations for humans to function, while high radiation levels could necessitate advanced shielding technologies. Beyond physical challenges, colonizing an exoplanet raises ethical and philosophical questions. If an exoplanet harbors its own ecosystem, what responsibilities would we have to preserve it? Would humanity's presence disrupt or endanger alien life forms, even microbial ones? These questions highlight the need for careful consideration as we expand our search for habitable worlds. Despite these challenges, the discovery of potentially habitable exoplanets fuels hope for the future. Projects like the Breakthrough Starshot Initiative aim to send tiny spacecraft to nearby star systems, providing our first direct observations of exoplanets. Meanwhile, ground-based telescopes like the Extremely Large Telescope, YELT, and space-based observatories like LUVOIR, Large Ultraviolet Optical Infrared Surveyor, promise to deepen our understanding of distant worlds. The study of exoplanets also offers profound insights into the nature of life itself. By examining a wide range of planetary environments, scientists can explore the limits of habitability and the potential diversity of life forms. Could life exist in conditions vastly different from Earth's, such as on planets with oceans of liquid methane or thick hydrogen atmospheres? These questions challenge our assumptions and broaden our perspective on what life could be. As we continue to discover new worlds, the possibility of finding life, or even a new home, becomes increasingly tangible. Each exoplanet tells a story about the processes that shape planetary systems and the potential for life to arise. Whether we ever set foot on an exoplanet or simply learn from afar, the exploration of these strange worlds deepens our connection to the cosmos. The search for exoplanets is not just a scientific endeavor, but a quest to understand our place in the universe. Are we alone, or are there other civilizations out there, perhaps looking back at us with the same curiosity? And if Earth ever becomes uninhabitable, could an exoplanet offer humanity a second chance? These questions drive our exploration, pushing the boundaries of what we know and inspiring us to dream of what lies beyond. The expansion of the universe, a race without a finish line. What drives the universe to keep expanding, and where will this relentless growth lead? From the moment of the Big Bang, the universe has been stretching outward, its galaxies and structures moving farther apart with time. Initially, scientists believed that gravity would eventually slow this expansion, possibly even reversing it. However, the discovery of dark energy, a mysterious force accelerating the universe's growth, has rewritten our understanding of its ultimate fate. But what does this expansion mean for the cosmos, and how does it shape everything we see? The expansion of the universe was first observed in the 1920s by Edwin Hubble, who discovered that galaxies are moving away from us, with more distant galaxies receding faster. This relationship, known as Hubble's law, provided the first direct evidence for an expanding universe. By extrapolating this motion backward, scientists determined that the universe originated from a single, incredibly dense and hot state roughly 13.8 billion years ago. Initially, astronomers expected the expansion to slow over time due to the gravitational pull of matter. However, observations of distant supernovae in the late 1990s revealed something astonishing. The expansion of the universe is not decelerating, it's accelerating. This unexpected discovery led to the introduction of dark energy, a mysterious form of energy that makes up about 68% of the universe and drives its accelerated growth. Dark energy remains one of the greatest mysteries in modern physics. It appears to act as a repulsive force, counteracting gravity on cosmic scales. Some theories propose that it is a property of spacetime itself, represented by the cosmological constant in Einstein's equations. Others suggest it might be a dynamic field, similar to the one responsible for cosmic inflation during the universe's earliest moments. Determining the true nature of dark energy is a central goal of modern cosmology. The effects of expansion are profound. On a local scale, the gravitational forces within galaxies and clusters of galaxies are strong enough to overcome expansion, keeping these structures intact. However, on larger scales, expansion dominates, driving galaxies apart and creating vast regions of empty space known as cosmic voids. Over billions of years, the universe has grown increasingly structured, with matter clustering into a web of filaments and nodes surrounded by these voids. But the story of expansion is not static. The rate of expansion, described by the Hubble constant, has varied over time and continues to evolve. Early in the universe's history, the expansion was dominated by radiation and matter, which slowed its growth. However, as the universe aged and thinned out, dark energy took over, accelerating the expansion. Today, the exact value of the Hubble constant remains a topic of intense debate, with different measurement methods yielding slightly different results. Resolving this discrepancy could reveal new physics beyond our current understanding. As the universe expands, its temperature decreases, and its contents spread out. This cooling and dilution have profound implications for the cosmos. For example, as the universe grows older, the formation of new stars will slow, and galaxies will eventually run out of the gas needed to sustain stellar birth. Over trillions of years, the universe could become a dark, starless expanse, a scenario known as the Big Freeze. Alternatively, if dark energy grows stronger over time, it could lead to a Big Rip. In this scenario, the expansion would accelerate so dramatically that it would tear apart galaxies, stars, planets, and even atoms, reducing the universe to a featureless void. Conversely, if dark energy weakens or reverses, the expansion might halt, leading to a big crunch, where the universe collapses back into a singularity. Despite these daunting possibilities, the study of cosmic expansion provides valuable insights into the nature of the universe. For instance, by observing the distribution of galaxies and their motion, astronomers can reconstruct the universe's history and test theories about its composition and evolution. Tools like the Sloan Digital Sky Survey and the Dark Energy Survey have mapped millions of galaxies, revealing the large-scale structure of the cosmos and the effects of dark energy over time. Future missions promise even greater discoveries. The Euclid Space Telescope, for example, will create detailed 3D maps of the universe, tracing the influence of dark energy and dark matter. Similarly, the Vera C. Rubin Observatory will survey the entire sky, measuring the positions and movements of billions of galaxies to refine our understanding of expansion. The expansion of the universe also challenges our perceptions of reality. How can space itself expand, and what lies beyond the observable universe? Some theories suggest that the universe might be infinite, with no edge to its growth. Others propose that it could be finite, but but unbounded, like the surface of a sphere, where traveling in one direction long enough would bring you back to your starting point. These possibilities highlight the profound mysteries surrounding the nature of space and time. One of the most intriguing implications of cosmic expansion is its connection to the multiverse. If our universe is one of many, as some theories suggest, its expansion might be just one chapter in a larger, eternal process of creation and destruction. Each universe could have its own rate of expansion, driven by different physical laws and constants. For now, the expansion of the universe remains a race without a finish line, a constant reminder of the dynamic and evolving nature of the cosmos. As galaxies drift apart and the universe grows colder, we are left to ponder the forces shaping this grand expansion and what they reveal about the ultimate fate of existence. What might the future hold for a universe that refuses to stand still? The answers lie in the vast, growing emptiness of space, waiting for us to explore. The secrets hidden in nebulae. What celestial mysteries lie within the glowing clouds of gas and dust scattered across the universe? Nebulae, the vast and colorful nurseries of stars, are among the most visually striking and scientifically intriguing structures in the cosmos. These ethereal formations are more than just stunning spectacles. They are key to understanding the birth, life, and death of stars, as well as the chemical enrichment of the universe. But what exactly are nebulae, and what secrets do they hold? Nebulae come in many forms, each playing a unique role in the cosmic cycle. They are composed primarily of hydrogen, along with smaller amounts of helium, oxygen, carbon, and other elements. These elements, created in the cores of stars and released during their death, form the raw material for new stars and planets. In essence, nebulae are both the remnants of stars that have lived and the cradles of stars yet to be born. The most famous type of nebula is the stellar nursery, where stars are formed from dense regions of gas and dust. These regions, known as molecular clouds, can stretch for hundreds of light years and contain enough material to create thousands of stars. Under the influence of gravity, clumps within these clouds collapse, heating up and forming protostars, the precursors to fully fledged stars. The Orion Nebula, located about 1,350 light-years away, is a prime example of a stellar nursery, offering astronomers a front-row seat to the process of star formation. As stars form, their radiation and stellar winds sculpt the surrounding gas and dust, creating intricate patterns of light and shadow. These interactions give nebulae their characteristic beauty, with colors determined by the types of gases present. For example, hydrogen emits red light, while oxygen glows green or blue. Observatories like the Hubble Space Telescope have captured these nebulae in stunning detail, revealing structures that look almost otherworldly. Another type of nebula is the planetary nebula, which forms when a star like the Sun reaches the end of its life. As the star exhausts its nuclear fuel, it sheds its outer layers, leaving behind a hot core known as a white dwarf. The expelled material expands outward, creating intricate shells of gas that are illuminated by the ultraviolet radiation of the white dwarf. Despite their name, planetary nebulae have nothing to do with planets. The term originates from their round appearance in early telescopes. Examples like the Helix Nebula and the Ring Nebula showcase the complexity of stellar death and the beauty of this final stage. In more violent circumstances, nebulae can form as a result of supernova explosions. When a massive star reaches the end of its life, it undergoes a catastrophic collapse, releasing its outer layers in a spectacular blast. The resulting supernova remnant is a rapidly expanding shell of gas and dust, enriched with heavy elements forged in the star's core. These remnants, like the Crab Nebula, are not just visually impressive. They are also key to understanding how elements like gold, silver, and iron are distributed throughout the galaxy. Nebulae are also crucial for understanding the chemical evolution of the universe. Early in the universe's history, only the lightest elements, hydrogen, helium, and a trace of lithium, were created in the Big Bang. Heavier elements, essential for life and planets, were forged in the cores of stars and scattered into space by supernovae and stellar winds. These elements mix into nebulae, enriching the gas clouds that will eventually form new stars and planetary systems. In this way, nebulae act as cosmic recycling centers, transforming the remnants of old stars into the building blocks of new ones. Nebulae also hold clues about the dynamics of the interstellar medium, the vast space between stars. Their structures often reveal the effects of powerful forces, such as shock waves from supernovae or the intense radiation of young stars. By studying nebulae, astronomers can trace these forces and understand how they shape the galaxy as a whole. One of the most mysterious types of nebulae is the dark nebula, which appears as a void against the backdrop of stars. These dense regions of gas and dust block light, hiding what lies within. The Horsehead Nebula is a striking example, its silhouette stark against the glowing clouds behind it. Though they appear empty, dark nebulae are often the sites of active star formation, concealing young stars and protostars within their shrouded interiors. Modern astronomy has revealed even more about nebulae through spectroscopy, which analyzes the light emitted or absorbed by these clouds. This technique allows scientists to determine their chemical composition, temperature, density, and motion. For instance, by studying the spectra of the Orion Nebula, astronomers have identified the presence of complex organic molecules, building blocks that could play a role in the origins of life. Nebulae are not just fascinating scientifically, they also challenge our perceptions of scale and time. Their vastness is difficult to comprehend. Some span hundreds of light years, while the processes occurring within them unfold over millions of years. Yet, they also connect us to the cosmos in a profound way. The very atoms that make up our bodies were once part of a nebula, forged in the heart of a star, and scattered into space before coalescing into Earth. As we continue to study nebulae, new questions arise. What triggers the collapse of a molecular cloud into stars? How do magnetic fields influence the structure of nebulae? And could the organic molecules within these clouds seed the development of life on newly formed planets? These mysteries drive ongoing exploration, pushing the boundaries of what we know about the universe. Nebulae remind us that the cosmos is a place of constant transformation. They are both the remnants of what has been and the promise of what is yet to come, bridging the gap between destruction and creation. By unraveling their secrets, we gain a deeper understanding of the forces that shape the universe and our own place within it. The missing antimatter puzzle. Why is our universe dominated by matter when it should contain equal amounts of matter and antimatter? This profound mystery, often called the missing antimatter problem, has perplexed physicists for decades. According to the standard model of particle physics, the Big Bang should have produced equal quantities of matter and antimatter, which would have annihilated each other in a flash of energy. Yet, the observable universe is overwhelmingly composed of matter, with antimatter seemingly vanishing from existence. Where did it go, and what does its absence reveal about the origins of the cosmos? To understand the missing antimatter problem, we must first explore the nature of antimatter. Every particle of matter has an antimatter counterpart with the same mass but opposite electric charge. For instance, the antimatter counterpart of an electron is a positron, which carries a positive charge instead of a negative one. When matter and antimatter collide, they annihilate, converting their mass into pure energy according to Einstein's famous equation, E equals mc2 E equals mc caret 2 E equals mc2. In theory, the Big Bang should have created a perfectly symmetrical universe with equal amounts of matter and antimatter. As these particles met and annihilated, the universe should have been left with nothing but photons. Yet, for reasons still not fully understood, this didn't happen. Somehow, a tiny imbalance arose, with slightly more matter than antimatter surviving the annihilation process. This slight excess of matter, just one particle in a billion, accounts for all the stars, galaxies, planets, and life we see today. The key to solving this puzzle lies in understanding why this imbalance occurred. Physicists refer to this phenomenon as baryon asymmetry, and several theories attempt to explain it. One leading idea is that the laws of physics may not treat matter and antimatter identically, a concept known as CP violation, charge parity violation. CP violation occurs when certain particles behave differently from their antiparticles, introducing a bias that could have favored matter during the universe's early moments. Evidence for CP violation has been observed in experiments involving subatomic particles called mesons, which exhibit slight differences in the way they decay compared to their antimatter counterparts. However, the amount of CP violation observed so far is not sufficient to explain the overwhelming dominance of matter in the universe. This discrepancy suggests that there may be additional, undiscovered sources of CP violation or entirely new physics beyond the standard model. Another intriguing possibility involves neutrinos, ghostly particles that interact so weakly with matter that trillions pass through your body every second unnoticed. Neutrinos come in 3 flavors and can oscillate between them as they travel. If neutrinos and their antimatter counterparts exhibit different oscillation patterns, this could provide a mechanism for the matter-antimatter imbalance. Experiments like the Deep Underground Neutrino Experiment, DUNE, aim to explore this possibility, offering hope for new insights into the missing antimatter puzzle. The absence of antimatter also raises questions about its possible hiding places. Could pockets of antimatter exist in remote regions of the universe? While this idea is intriguing, it faces significant challenges. If antimatter galaxies or clusters existed, they would emit characteristic gamma rays at their boundaries, where antimatter and matter interact. So far, no such signals have been detected, suggesting that antimatter is not simply hiding, but is genuinely scarce. Antimatter does, however, exist in small quantities in our universe. It is produced naturally in high-energy events like supernovae, gamma-ray bursts, and cosmic ray interactions. For example, antimatter particles are routinely detected in the form of positrons emitted by certain radioactive decays. Additionally, antimatter can be artificially created in laboratories and particle accelerators, where it plays a crucial role in medical imaging technologies like positron emission tomography, PET scans. The study of antimatter is not just a quest to solve a cosmic mystery. It has practical applications and profound implications for our understanding of the universe. For instance, if we could produce and store antimatter in significant quantities, it could serve as an incredibly efficient energy source. Just 1 gram of antimatter reacting with matter would release as much energy as the detonation of a nuclear bomb. While this remains far beyond current technological capabilities, the potential is tantalizing. The missing antimatter puzzle also connects to deeper questions about the nature of symmetry in physics. Symmetry principles, such as those governing the interactions of particles, are fundamental to our understanding of the universe. The apparent imbalance between matter and antimatter challenges these principles, suggesting that our current theories are incomplete. Resolving this mystery could lead to breakthroughs in our understanding of the universe's earliest moments and the fundamental forces that govern it. Recent advances in particle physics and cosmology offer hope for progress. Experiments at facilities like the Large Hadron Collider, LHC, continue to probe the behavior of particles and antiparticles, searching for new sources of CP violation and clues to the missing antimatter. Meanwhile, observations of the cosmic microwave background and large-scale structure of the universe provide indirect evidence for the conditions of the early cosmos, offering additional constraints on theories. The search for answers is also driving innovation in antimatter research. Projects like ALPHA at CERN aim to study the properties of antihydrogen, an atom composed of an antiproton and a positron, in unprecedented detail. By comparing the behavior of hydrogen and antihydrogen, scientists hope to uncover subtle differences that could explain the matter-antimatter asymmetry. The missing antimatter problem is more than just a puzzle. It's a doorway to new physics and a deeper understanding of the universe. Solving it could reveal the forces and processes that shape the cosmos, providing insights into everything from the formation of galaxies to the ultimate fate of the universe. What secrets might the universe be hiding in its missing antimatter? As we continue to explore this mystery, each discovery brings us closer to unlocking one of the greatest enigmas of existence: the missing antimatter puzzle. Why is our universe dominated by matter when it should contain equal amounts of matter and antimatter? This profound mystery, often called the missing antimatter problem, has perplexed physicists for decades. According to the standard model of particle physics, the Big Bang should have produced equal quantities of matter and antimatter, which would have annihilated each other in a flash of energy. Yet, the observable universe is overwhelmingly composed of matter, with antimatter seemingly vanishing from existence. Where did it go, and what does its absence reveal about the origins of the cosmos? To understand the missing antimatter problem, we must first explore the nature of antimatter. Every particle of matter has an antimatter counterpart with the same mass but opposite electric charge. For instance, the antimatter counterpart of an electron is a positron, which carries a positive charge instead of a negative one. When matter and antimatter collide, they annihilate, converting their mass into pure energy according to Einstein's famous equation: E equals mc2 E equals mc2 E equals mc2. In theory, the Big Bang should have created a perfectly symmetrical universe with equal amounts of matter and antimatter. As these particles met and annihilated, the universe should have been left with nothing but photons. Yet, for reasons still not fully understood, this didn't happen. Somehow, a tiny imbalance arose, with slightly more matter than antimatter surviving the annihilation process. This slight excess of matter, just one particle in a billion, accounts for all the stars, galaxies, planets, and life we see today. The key to solving this puzzle lies in understanding why this imbalance occurred. Physicists refer to this phenomenon as baryon asymmetry, and several theories attempt to explain it. One leading idea is that the laws of physics may not treat matter and antimatter identically, a concept known as CP violation, charge parity violation. CP violation occurs when certain particles behave differently from their antiparticles, introducing a bias that could have favored matter during the universe's early moments. Evidence for CP violation has been observed in experiments involving subatomic particles called mesons, which exhibit slight differences in the way they decay compared to their antimatter counterparts. However, the amount of CP violation observed so far is not sufficient to explain the overwhelming dominance of matter in the universe. This discrepancy suggests that there may be additional, undiscovered sources of CP violation or entirely new physics beyond the standard model. Another intriguing possibility involves neutrinos, ghostly particles that interact so weakly with matter that trillions pass through your body every second unnoticed. Neutrinos come in three flavors and can oscillate between them as they travel. If neutrinos and their antimatter counterparts exhibit different oscillation patterns, this could provide a mechanism for the matter-antimatter imbalance. Experiments like the Deep Underground Neutrino Experiment, DUNE, aim to explore this possibility, offering hope for new insights into the missing antimatter puzzle. The absence of antimatter also raises questions about its possible hiding places. Could pockets of antimatter exist in remote regions of the universe? While this idea is intriguing, it faces significant challenges. If antimatter galaxies or clusters existed, they would emit characteristic gamma rays at their boundaries, where antimatter and matter interact. So far, no such signals have been detected, suggesting that antimatter is not simply hiding, but is genuinely scarce. Antimatter does, however, exist in small quantities in our universe. It is produced naturally in high-energy events like supernovae, gamma-ray bursts, and cosmic ray interactions. For example, antimatter particles are routinely detected in the form of positrons emitted by certain radioactive decays. Additionally, antimatter can be artificially created in laboratories and particle accelerators, where it plays a crucial role in medical imaging technologies like positron emission tomography, PET scans. The study of antimatter is not just a quest to solve a cosmic mystery. It has practical applications and profound implications for our understanding of the universe. For instance, if we could produce and store antimatter in significant quantities, it could serve as an incredibly efficient energy source. Just 1 gram of antimatter reacting with matter would release as much energy as the detonation of a nuclear bomb. While this remains far beyond current technological capabilities, the potential is tantalizing. The missing antimatter puzzle also connects to deeper questions about the nature of symmetry in physics. Symmetry principles, such as those governing the interactions of particles, are fundamental to our understanding of the universe. The apparent imbalance between matter and antimatter challenges these principles, suggesting that our current theories are incomplete. Resolving this mystery could lead to breakthroughs in our understanding of the universe's earliest moments and the fundamental forces that govern it. Recent advances in particle physics and cosmology offer hope for progress. Experiments at facilities like the Large Hadron Collider, LHC, continue to probe the behavior of particles and antiparticles, searching for new sources of CP violation and clues to the missing antimatter. Meanwhile, observations of the cosmic microwave background and large-scale structure of the universe provide indirect evidence for the conditions of the early cosmos, offering additional constraints on theories. The search for answers is also driving innovation in antimatter research. Projects like ALPHA at CERN aim to study the properties of antihydrogen, an atom composed of an antiproton and a positron, in unprecedented detail. By comparing the behavior of hydrogen and antihydrogen, scientists hope to uncover subtle differences that could explain the matter-antimatter asymmetry. The missing antimatter problem is more than just a puzzle. It's a doorway to new physics and a deeper understanding of the universe. Solving it could reveal the forces and processes that shape the cosmos, providing insights into everything from the formation of galaxies to the ultimate fate of the universe. What secrets might the universe be hiding in its missing antimatter? As we continue to explore this mystery, each discovery brings us closer to unlocking one of the greatest enigmas of existence. Could we harvest energy from stars? What if the stars that light up the universe could also fuel our civilization? Stars, including our sun, are colossal powerhouses, radiating energy at unfathomable rates. As humanity's energy needs grow, the idea of harvesting energy directly from stars transitions from the realm of science fiction into a topic of serious scientific consideration. Could we harness the nearly infinite energy of stars to power advanced civilizations? And if so, how? Stars are fueled by nuclear fusion, a process where hydrogen nuclei fuse into helium under immense pressure and temperature, releasing vast amounts of energy in the form of light and heat. The Sun alone outputs around 3.8 by 10,263.8 times 10 carat 26, 3.8 times 1026 watts of energy every second, more than enough to meet humanity's energy demands millions of times over. Capturing even a fraction of this energy could revolutionize civilization, offering a sustainable power source for millennia. The concept of harvesting energy from stars on a massive scale was popularized by the theoretical Dyson sphere, a megastructure envisioned by physicist Freeman Dyson in 1960. A Dyson sphere is a hypothetical construct that completely or partially surrounds a star, capturing its energy output for use by an advanced civilization. Such a structure could take various forms, including a solid shell, a swarm of satellites, or a network of solar collectors orbiting the star. Building a Dyson sphere, however, presents monumental challenges. The sheer scale of such a project would require materials far beyond Earth's current capabilities, likely necessitating the mining of entire planets or asteroids. Additionally, maintaining the structural integrity of a Dyson sphere would be nearly impossible due to gravitational forces, solar winds, and the star's radiation pressure. For these reasons, many scientists consider a Dyson swarm, a vast array of solar-collecting satellites in orbit around the star, a more plausible alternative. The energy captured by a Dyson swarm could be transmitted back to a home planet using wireless technologies such as microwaves or lasers. This would eliminate the need for physical energy transport, but would still face significant hurdles, including potential energy losses during transmission and the risk of misaligned beams causing catastrophic damage. A less ambitious and more immediately feasible approach is harvesting solar energy from our sun using space-based solar power systems. Satellites equipped with solar panels could collect sunlight unimpeded by Earth's atmosphere, which absorbs and scatters a significant portion of solar radiation. The energy could then be beamed to Earth using microwave or laser transmission. Unlike a Dyson swarm, space-based solar power systems could be implemented with current technology and would offer a scalable solution to humanity's energy needs. Looking beyond our solar system, the concept of stellar energy harvesting raises intriguing possibilities for interstellar exploration and colonization. A civilization expanding into space could build energy-collecting structures around multiple stars, creating an interstellar energy network. This network could power advanced propulsion systems for spacecraft, making long-term interstellar travel and the colonization of distant worlds more feasible. The potential to harvest energy from stars also ties into the search for extraterrestrial intelligence, SETI. Advanced civilizations capable of constructing Dyson spheres or swarms would emit detectable infrared radiation due to waste heat. Astronomers have already begun searching for these signatures using telescopes like the Wide Field Infrared Survey Explorer, WISE, though no definitive evidence of such structures has been found so far. If detected, these megastructures would provide direct evidence of technologically advanced alien civilizations. Harvesting stellar energy comes with ethical and philosophical implications as well. Should humanity prioritize using resources to build such structures, or focus on conserving and improving energy efficiency on Earth? Additionally, altering a star's energy output could have unforeseen consequences for any nearby ecosystems or planets, raising questions about our responsibility as stewards of the cosmos. In addition to direct energy harvesting, stars offer other potential energy sources. Stellar winds, streams of charged particles emitted by stars, could be harnessed using magnetic sails, much like wind turbines capture wind energy on Earth. Similarly, capturing the radiation from solar flares, though technically challenging, could provide bursts of high-energy output. Another exciting frontier is the possibility of harvesting energy from dying stars. As stars exhaust their nuclear fuel, they undergo dramatic transformations, such as collapsing into neutron stars or black holes. These objects possess extreme energy environments, where processes like accretion and relativistic jets release enormous amounts of power. Capturing this energy would require highly advanced technologies capable of withstanding extreme gravitational and radiation forces. At the most speculative edge of science, some theorists have proposed the idea of tapping into the energy of a star directly via controlled fusion. By extracting hydrogen or other fusible material from a star and using it in fusion reactors, a civilization could theoretically sustain itself for billions of years. However, the technical and logistical challenges of such an endeavor are immense, requiring a level of engineering sophistication far beyond what humanity currently possesses. Despite these challenges, the idea of harvesting energy from stars aligns with humanity's long-term aspirations to become a spacefaring civilization. As we explore and settle new worlds, access to abundant energy will be crucial for sustaining life, advancing technology, and achieving our full potential as a species. The stars have fueled our imagination for millennia, serving as both literal and figurative beacons of hope and possibility. Harnessing their energy represents the next step in our journey to understand and utilize the universe's resources. It raises profound questions about our capabilities, responsibilities, and future as a species. Will we one day look to the stars not just for inspiration, but as the ultimate source of energy to propel us into the future? Supernovae, the explosive death of stars. What happens when a star meets its spectacular end? Supernovae, the dramatic explosions marking the death of certain stars, are among the most powerful and transformative events in the universe. They release staggering amounts of energy, outshining entire galaxies for brief periods, and scatter the elements forged in stars into space. These cataclysmic events are not just endings. They are beginnings, seeding the cosmos with the raw materials for new stars, planets, and even life itself. But what triggers a supernova, and what can these cosmic detonations teach us about the universe? Supernovae occur under two main scenarios: the death of a massive star, or the explosive reignition of a white dwarf. Both processes involve the rapid release of energy, but the mechanisms and outcomes differ dramatically. In the first scenario, a core collapse supernova occurs when a massive star, typically more than 8 times the mass of the Sun, exhausts its nuclear fuel. For most of its life, a star maintains a delicate balance between the outward pressure of nuclear fusion and the inward pull of gravity. But once the star can no longer fuse heavier elements, its core collapses under its own weight, reaching densities comparable to those of an atomic nucleus. This collapse triggers a rebound effect, sending shock waves outward and tearing the star apart in a violent explosion. The aftermath of a core collapse supernova depends on the mass of the original star. If the remnant core is below a certain mass threshold, it becomes a neutron star, a city-sized object of extraordinary density, composed almost entirely of neutrons. Neutron stars can exhibit extreme behaviors, such as spinning rapidly and emitting beams of radiation, becoming pulsars. If the remnant core is even more massive, it collapses further into a black hole, a region of space-time so warped by gravity that nothing, not even light, can escape. The second type of supernova, a thermonuclear supernova, occurs in binary star systems. In these systems, a white dwarf, the dense remnant of a low or medium-mass star, can siphon material from its companion star. If the white dwarf accumulates enough mass to exceed the Chandrasekhar limit, about 1.4 times the mass of the Sun, it undergoes a runaway nuclear reaction, obliterating itself in a fiery explosion. These thermonuclear supernovae are essential for measuring cosmic distances, as their consistent brightness makes them reliable standard candles for determining how far away galaxies are. Supernovae are not just spectacular, they are essential to the evolution of the universe. These explosions forge and distribute heavy elements, such as carbon, oxygen, and iron, which are critical for life. Without supernovae, the universe would lack the rich chemical diversity needed for planets and living organisms. Every atom of calcium in your bones and iron in your blood was created in the heart of a dying star and dispersed into space by a supernova. The energy and radiation released during a supernova also play a vital role in shaping the galaxy. The shock waves from these explosions compress surrounding gas clouds, triggering new waves of star formation. At the same time, the intense radiation can strip planets of their atmospheres and sterilize nearby regions, demonstrating the dual nature of supernovae as agents of both creation and destruction. Supernovae are also key to understanding some of the most extreme environments in the universe. For instance, they are responsible for producing cosmic rays, high-energy particles that travel through space at nearly the speed of light. By studying cosmic rays, scientists gain insights into the processes that accelerate particles to such incredible speeds, as well as the effects of these particles on planetary atmospheres and ecosystems. Observing supernovae is both challenging and rewarding. They occur unpredictably and are visible for only a short time, but modern telescopes and surveys have made it easier to catch these fleeting events. For example, automated sky surveys like the Zwicky Transient Facility, ZTF, and Pan-STARRS scan the skies nightly, detecting supernovae in distant galaxies. These observations provide invaluable data about the rate and distribution of supernovae, helping scientists refine their models of stellar evolution and galactic dynamics. One of the most famous supernovae in human history, SN 1987A, occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. It provided an unprecedented opportunity for observation, yielding insights into the physics of supernova explosions and the behavior of neutrinos, elusive particles released in vast quantities during a supernova. The study of SN 1987A continues to inform our understanding of these events decades later. Supernovae also have a direct connection to our own solar system. Evidence suggests that nearby supernovae may have triggered the formation of the Sun and its planetary system by compressing the gas and dust in a molecular cloud. Additionally, radioactive isotopes found in meteorites indicate that one or more supernovae occurred near the young solar system, seeding it with the elements necessary for planetary formation. Despite our advances in understanding supernovae, many questions remain. For example, the exact mechanisms of core collapse supernovae are still not fully understood, particularly the processes that allow the shock wave to successfully propagate through the collapsing star. Similarly, the role of magnetic fields and rotation in shaping the explosion remains an area of active research. Supernovae also challenge us to think about the long-term future of the universe. As stars evolve and die, they leave behind neutron stars, black holes, and the dispersed remnants of their explosions. Over billions of years, the universe will accumulate these relics, shaping its ultimate fate. In studying supernovae, we confront both the violent and creative forces of the cosmos. These explosions remind us that destruction and renewal are intertwined, not just in the universe, but in life itself. Each supernova is a cosmic heartbeat, a fleeting yet transformative event that reverberates across space and time. What new discoveries might future supernovae bring? As we develop more advanced observatories and techniques, the answers may illuminate not only the life cycles of stars but also the nature of the universe itself. Are we part of a galactic civilization? Could humanity be just one small part of a larger, interconnected galactic civilization? As we look to the stars, the question of whether intelligent life exists elsewhere in the Milky Way takes on profound significance. If other advanced civilizations are out there, what might they look like, and how would they interact with one another, or with us? The idea of a galactic civilization, a network of advanced societies spanning star systems, is both tantalizing and challenging. But what evidence do we have for its existence, and what might it mean for humanity's place in the cosmos? The search for extraterrestrial intelligence, SETI, has long been guided by the assumption that intelligent life might leave detectable traces. These could take the form of radio signals, laser pulses, or even megastructures like Dyson spheres, built to harness the energy of stars. Yet, despite decades of scanning the skies, no clear evidence of such signals has emerged. This apparent silence, often referred to as the Fermi paradox, raises the question: if the galaxy is teeming with intelligent life, why haven't we found it? One possible answer is that intelligent civilizations may operate on timescales far beyond our comprehension. The Milky Way is over 13 billion years old, while humanity's technological era spans just a few centuries. Advanced civilizations may rise and fall over eons, their signals fleeting and easily missed. Alternatively, they might exist in forms we cannot detect, such as post-biological entities, advanced artificial intelligences that communicate in ways imperceptible to us. Another explanation is the rare Earth hypothesis, which posits that the conditions necessary for intelligent life are so specific that Earth may be a unique or extremely rare case. Factors such as a stable climate, the presence of liquid water, and the protection of a large moon and magnetic field could make planets like Earth exceedingly uncommon. If this hypothesis is correct, humanity might truly be alone, or one of only a few intelligent species in the galaxy. Yet, the possibility of a galactic civilization remains compelling. Such a civilization could take many forms, from loose networks of independent societies to highly organized federations spanning multiple star systems. If communication between star systems is possible, these civilizations might exchange knowledge, trade resources, or collaborate on large-scale projects, such as exploring the galaxy or managing its resources. The concept of the Kardashev scale provides a framework for understanding the technological capabilities of advanced civilizations. Proposed by Russian astrophysicist Nikolai Kardashev, this scale categorizes civilizations based on their energy usage. Type 1 civilizations harness the energy of their home planet. Type 2 civilizations capture the energy of their star, perhaps using a Dyson sphere. Type 3 civilizations command the energy of an entire galaxy. Humanity, currently a Type 0 civilization, has yet to fully harness Earth's energy resources, but the prospect of advancing to higher levels raises intriguing possibilities. A Type 2 or Type 3 civilization would possess technologies far beyond our imagination, enabling interstellar communication, terraforming, and even the manipulation of space-time. If such civilizations exist, their members might not resemble humans at all. Life on Earth has evolved in response to specific environmental pressures, but alien life forms would arise under entirely different conditions. They might be silicon-based instead of carbon-based, or they could thrive in environments humans would find inhospitable, such as the atmospheres of gas giants or the icy oceans of moons like Europa. Communication between civilizations would face significant challenges, including vast distances and differences in biology, language, and culture. Nevertheless, efforts like the Arecibo message and the Voyager Golden Records represent humanity's attempts to reach out, sending encoded messages into space in the hope that someone might someday find and understand them. One intriguing possibility is that advanced civilizations might deliberately avoid contact with less developed societies, adhering to a kind of galactic prime directive. This concept, often explored in science fiction, suggests that more advanced civilizations might choose to observe emerging species like humanity from a distance, avoiding interference until we reach a certain level of technological or cultural maturity. Alternatively, The lack of evidence for a galactic civilization could be due to the sheer difficulty of interstellar communication and travel. The distances between stars are immense, and even at light speed, sending a message across the galaxy could take tens of thousands of years. Technologies like warp drives or wormholes, while theoretically possible, remain speculative and may be beyond the reach of even advanced civilizations. Despite these challenges, the idea of a galactic civilization invites us to think about humanity's future. If we survive our current challenges and continue to advance technologically, we could one day join the ranks of an interstellar network. This would require overcoming significant hurdles, including developing sustainable energy sources, achieving interstellar travel, and fostering global cooperation. The search for a galactic civilization also prompts deeper questions about the nature of intelligence and consciousness. Are advanced civilizations more likely to prioritize exploration, cooperation, or self-preservation? Do they seek knowledge for its own sake? Or are they driven by needs and desires similar to our own? These questions reveal as much about humanity as they do about the cosmos, challenging us to consider what it means to be intelligent and what kind of civilization we want to become. Ultimately, the search for a galactic civilization is a journey of discovery, both outward and inward. Whether or not we find evidence of intelligent life beyond Earth, the quest itself expands our understanding of the universe and our place within it. It encourages us to imagine what is possible, to explore the unknown, and to aspire to a future that transcends our limitations. Could humanity one day become part of a vast, interconnected galactic community? The answer may lie in the stars, waiting for us to find it. The Fermi paradox. Where is everyone? If the universe is so vast and ancient, filled with countless stars and planets, why haven't we found any evidence of intelligent extraterrestrial life? This haunting question, known as the Fermi paradox, challenges our assumptions about the universe and our place within it. Despite decades of searching, humanity has yet to encounter any sign of advanced civilizations. No radio signals, no spacecraft, no cosmic megastructures. Is the universe teeming with life but silent? Or is intelligence an extraordinarily rare phenomenon? To unravel the paradox, we must consider the possibilities, each more intriguing and unsettling than the last. The paradox was named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a 1950 conversation about extraterrestrial life. Fermi's question highlights a striking inconsistency. If intelligent life is common and capable of interstellar communication or travel, we should have detected some evidence of it by now. The Milky Way alone contains over 100 billion stars, many of which host planetary systems. With billions of years of cosmic history to account for, advanced civilizations should have had ample time to spread across the galaxy. Yet the silence persists. One explanation for the Fermi paradox is that life itself might be exceedingly rare. While microbial life seems plausible under the right conditions, the leap from simple organisms to intelligent beings capable of technology might require an extraordinary combination of factors. This idea aligns with the rare Earth hypothesis, which argues that Earth's conditions, such as its stable climate, protective magnetic field, and the presence of a large moon, are uniquely suited to fostering complex life. Another possibility is that intelligent life frequently arises, but tends to self-destruct before achieving interstellar communication or travel. This grim scenario is known as the Great Filter, a hypothetical barrier that prevents civilizations from reaching an advanced stage. The Great Filter could occur at any point in a civilization's development, from the origin of life to the ability to manage advanced technologies. For humanity, it raises the unsettling question: have we already passed the Great Filter, or is it still ahead of us? Alternatively, intelligent civilizations might simply choose not to communicate. This could be due to philosophical or ethical reasons, such as a galactic zoo hypothesis, where advanced species deliberately avoid interfering with less developed civilizations. In this scenario, humanity might be under observation, akin to animals in a nature reserve with no idea of the greater galactic society surrounding us. Another explanation is the immense challenge of interstellar communication and travel. The distances between stars are staggering, and even at the speed of light, messages would take years or millennia to travel between civilizations. Advanced societies might conclude that the energy and resources required for interstellar exploration outweigh the benefits, choosing instead to focus on their own star systems. The paradox also invites speculation about the nature of advanced civilizations. If they exist, they might not resemble humanity at all. They could be post-biological entities such as artificial intelligences with goals and behaviors incomprehensible to us. Alternatively, they might operate on timescales so long that human history appears as a fleeting moment, making communication or contact unlikely. Efforts to address the Fermi paradox have led to groundbreaking initiatives in the search for extraterrestrial intelligence (SETI). Projects like Breakthrough Listen scan the skies for artificial radio signals, while telescopes like the James Webb Space Telescope seek signs of life in the atmospheres of exoplanets. Despite these efforts, no definitive evidence of extraterrestrial intelligence has been found, deepening the mystery. Some theorists propose that the answer to the paradox may lie in our expectations. Perhaps we are looking for the wrong kinds of signals, or assuming that alien civilizations would behave in ways similar to us. For instance, instead of searching for radio signals, we might consider looking for technosignatures, such as waste heat from megastructures or chemical pollutants in planetary atmospheres. These indirect markers could provide evidence of advanced technologies without relying on intentional communication. The paradox also forces us to confront humanity's own trajectory. If we eventually develop the ability to colonize other star systems, what kind of civilization would we become? Would we choose to explore and communicate with other species? Or would we prioritize self-preservation and isolation? The answers to these questions could shape our approach to the search for extraterrestrial life and our understanding of our responsibilities as a cosmic species. Ultimately, the Fermi paradox is a mirror, reflecting both the limitations of our knowledge and the boundless possibilities of the universe. It challenges us to think beyond Earth, to imagine the many forms life and intelligence might take, and to consider what it means to be alone or not alone in the cosmos. Could the silence be temporary, a cosmic void awaiting its first signal, or is it permanent, a testament to the rarity of intelligent life? As we continue to search, each discovery brings us closer to answering this profound question. Where is everyone? Black hole energy. Can we harness the power of the void? What if the universe's most enigmatic objects, black holes, could become humanity's ultimate energy source? Black holes are known for their extraordinary gravitational pull, capable of warping space-time and swallowing anything that ventures too close. Yet, beneath their dark and fearsome exterior lies the potential for incredible power. From their spinning accretion disks to the energy radiated by their event horizons, black holes may hold the key to energy generation on an unimaginable scale. Could we one day tap into this cosmic reservoir? And if so, how? Black holes are formed when massive stars collapse under their own gravity, compressing their cores into regions so dense that not even light can escape. Despite their reputation as inescapable traps, black holes are not entirely isolated from the universe. They interact with their surroundings in ways that generate staggering amounts of energy, offering theoretical possibilities for energy extraction. One of the most promising ideas involves the accretion disk, the swirling ring of superheated gas and dust that orbits a black hole before crossing its event horizon. As matter in the disk spirals inward, it accelerates to incredible speeds, heating up to millions of degrees and emitting intense radiation, including X-rays. This process converts up to 10% of the matter's mass into energy, far surpassing the efficiency of nuclear fusion, which converts only about 0.7% of mass into energy. A civilization capable of harnessing this radiation could power entire planets, or even interstellar colonies. Another intriguing method for energy extraction involves the Penrose process, named after physicist Roger Penrose. This process takes advantage of a black hole's ergosphere, the region just outside the event horizon where space-time is twisted by the black hole's spin. In the Penrose process, a particle entering the ergosphere can split into two, with one fragment falling into the black hole and the other escaping with more energy than the original particle. The escaping fragment's energy gain comes at the expense of the black hole's rotational energy, effectively mining energy from the black hole's spin. The Blanford's-Najac process offers another possibility, leveraging the magnetic fields generated by a spinning black hole and its surrounding plasma. This process can channel energy outward in the form of powerful jets, which are often observed in active galactic nuclei and quasars. By capturing the energy in these jets, an advanced civilization could theoretically tap into one of the universe's most potent power sources. Black holes also radiate energy through a phenomenon called Hawking radiation, predicted by physicist Stephen Hawking. According to quantum theory, pairs of virtual particles continuously form and annihilate near the event horizon of a black hole. Occasionally, one particle escapes while the other is captured, resulting in a net loss of mass for the black hole. Over immense timescales, this radiation causes the black hole to evaporate entirely. While Hawking radiation is minuscule for large black holes, microscopic black holes, if they exist, could radiate energy at a much higher rate, offering another potential energy source. Despite these tantalizing prospects, harnessing black hole energy would require technological capabilities far beyond our current understanding. Constructing massive energy-collecting structures, such as Dyson spheres around black holes or advanced spacecraft capable of operating near their event horizons, presents extraordinary engineering challenges. Additionally, the intense radiation and gravitational forces near black holes pose significant risks to any devices or organisms attempting to extract energy. Another challenge lies in finding black holes suitable for energy harvesting. Stellar mass black holes, formed from the collapse of massive stars, are relatively common in the galaxy, but their energy output is limited compared to supermassive black holes found at the centers of galaxies. These cosmic giants, millions or billions of times the mass of the Sun, offer far greater energy potential, but are located vast distances from Earth. If humanity or another advanced civilization could overcome these obstacles, the implications would be profound. Black hole energy could provide a virtually limitless power source, enabling interstellar travel, terraforming, and the construction of massive infrastructure projects. It could also reduce dependence on traditional energy sources, transforming how civilizations interact with their environments. The pursuit of black hole energy also intersects with broader questions about the nature of black holes and their role in the universe. By studying how black holes generate and radiate energy, scientists could gain insights into fundamental physics, including the unification of quantum mechanics and general relativity. These investigations might even reveal new phenomena, such as exotic particles or previously unknown forces. The concept of black hole energy also features prominently in discussions about advanced extraterrestrial civilizations. A Type 2 or Type 3 civilization on the Kardashev scale, capable of harnessing the energy of stars or galaxies, might view black holes as prime energy sources. Detecting technosignatures, such as unusual energy emissions or structures near black holes, could provide indirect evidence of such civilizations. Philosophically, the idea of harnessing black hole energy challenges our perceptions of power and control. Black holes, long viewed as symbols of destruction and finality, could become tools for creation and growth. This transformation mirrors humanity's broader journey of understanding and mastering natural forces, turning what once seemed fearsome into something useful. As we explore the possibilities of black hole energy, we are reminded of the universe's vast potential and humanity's capacity for ingenuity. While the road to harvesting such energy is fraught with challenges, the rewards could redefine our relationship with the cosmos. Could black holes, the ultimate cosmic enigmas, one day fuel humanity's ambitions among the stars? The answer may lie in the future of exploration and discovery, where science and imagination meet. White holes, the reverse of black holes, or something more. If black holes represent cosmic traps from which nothing can escape, could their theoretical opposites, white holes, exist as gateways for matter and energy? First proposed as a mathematical counterpart to black holes in Einstein's theory of general relativity, white holes are hypothetical regions of spacetime that expel matter and energy, but allow nothing to enter. These mysterious objects challenge our understanding of the universe and raise fascinating questions about the nature of space-time, causality, and the ultimate fate of matter. White holes emerged as a solution to Einstein's equations, where time is effectively reversed compared to a black hole. While a black hole pulls everything inward toward its event horizon, a white hole pushes everything outward, creating a one-way barrier in the opposite direction. In theory, white holes could appear as intensely bright objects, spewing out radiation and matter while preventing anything from entering their boundaries. But do white holes exist in the real universe, or are they merely mathematical abstractions? So far, no definitive evidence of a white hole has been observed, and their existence remains speculative. However, their potential implications are profound, linking them to black holes, wormholes, and even the origins of the universe. One of the most intriguing ideas involves the relationship between black holes and white holes. In some theoretical models, a black hole could be connected to a white hole through a wormhole, a tunnel-like structure that bridges two regions of spacetime. Matter falling into a black hole in one location might emerge from a white hole in another, bypassing the intervening space. While wormholes remain hypothetical, their connection to white holes offers a tantalizing possibility for interstellar travel and time manipulation. Another proposal suggests that white holes might be tied to the process of black hole evaporation. As black holes lose mass through Hawking radiation over immense timescales, their event horizons shrink. Some theories speculate that at the final moment of evaporation, a black hole could transition into a white hole, ejecting its remaining mass and energy back into the universe. This process would preserve information, addressing one of the most vexing problems in theoretical physics: the black hole information paradox. White holes also have implications for the early universe. Some cosmologists have proposed that the Big Bang itself might have been a white hole. In this view, the universe could have emerged from a white hole-like event, with all the matter and energy expelled in the initial moments of cosmic inflation. If true, this would redefine our understanding of the universe's origins, linking it to the enigmatic physics of extreme spacetime. Despite their theoretical allure, white holes face significant challenges. One issue is their stability. Any disturbance in the surrounding spacetime could cause a white hole to collapse or transform into a black hole. Additionally, white holes appear to violate the second law of thermodynamics, which states that entropy, disorder, must always increase over time. A white hole, by reversing the flow of time locally, would seemingly decrease entropy, contradicting this fundamental principle. Observationally, the search for white holes is difficult due to their hypothetical nature and the lack of clear predictions about their signatures. However, some phenomena in the universe might hint at their existence. For instance, certain high-energy gamma-ray bursts or unexplained astrophysical phenomena could, in principle, be linked to white hole activity. Identifying these signals requires advanced instruments and creative interpretations of data. The study of white holes also intersects with the search for a unified theory of quantum gravity, a framework that combines general relativity with quantum mechanics. White holes, as extreme objects, push the limits of our understanding of spacetime, offering a unique testing ground for new theories. If white holes are more than mathematical curiosities, their discovery could revolutionize our understanding of the universe's structure and evolution. Philosophically, white holes challenge our perception of time and causality. If they exist, they represent regions of the universe where the arrow of time flows in reverse, defying our intuitive understanding of cause and effect. This reversal invites questions about the nature of time itself. Is it an absolute dimension, or is it a relative phenomenon shaped by the fabric of spacetime? The possibility of white holes also inspires speculation about their potential uses. Could an advanced civilization harness the energy expelled by a white hole, or even create one artificially as a source of power? Could white holes serve as gateways to other universes or alternate dimensions, offering new realms of exploration? For now, white holes remain in the realm of theoretical physics, tantalizing scientists with their potential while eluding direct observation. As our understanding of black holes deepens and our tools for exploring the cosmos improve, the possibility of discovering white holes, or ruling them out entirely, draws closer. Could white holes be the key to unlocking some of the universe's deepest mysteries? Or are they simply mathematical fantasies, glimpses of what might be possible in a reality far stranger than we can imagine? The fabric of space-time. Can we manipulate reality? What if we could bend, twist, or even tear the very fabric of space-time itself? Einstein's theory of general relativity revolutionized our understanding of the universe by showing that space and time are not fixed backdrops, but dynamic entities that respond to the presence of matter and energy. Massive objects like stars and black holes warp space-time, creating the gravitational fields we experience. But could humanity ever learn to manipulate space-time intentionally, unlocking the ability to travel faster than light, create wormholes, or even alter the flow of time? Space-time, as described by general relativity, is a four-dimensional continuum where three dimensions of space and one of time are interwoven. The key insight of Einstein's work is that gravity arises from the curvature of space-time. A massive object like the Sun bends space-time around it, causing smaller objects, such as planets, to follow curved paths, what we perceive as orbits. This framework not only explains the motion of celestial bodies, but also predicts phenomena like gravitational waves and time dilation, which have been confirmed through observation. But manipulating space-time goes far beyond understanding its properties. To alter space-time intentionally, we would need to control the factors that shape it: mass, energy, and momentum. For example, increasing or decreasing mass in a specific region could change the curvature of space-time, potentially redirecting the paths of objects or even light itself. Such control could have profound implications for transportation, communication, and exploration. One of the most famous proposals for manipulating space-time is the Alcubierre warp drive, a theoretical concept inspired by general relativity. Proposed by physicist Miguel Alcubierre in 1994, the warp drive envisions a spacecraft surrounded by a warp bubble that compresses space-time in front of it and expands space-time behind it. Inside the bubble, the spacecraft would remain stationary relative to the bubble itself, allowing it to travel faster than light without violating relativity. However, the Alcubierre drive faces significant challenges. It would require exotic matter with negative energy density, something not yet observed in nature, to stabilize the warp bubble. Additionally, the immense energy demands for such a drive are far beyond anything humanity can currently produce. Still, the concept remains a fascinating exploration of how space-time manipulation could enable interstellar travel. Another exciting possibility is the creation of wormholes, theoretical shortcuts through space-time that connect distant points. Wormholes, also known as Einstein-Rosen bridges, emerge naturally from the equations of general relativity under certain conditions. If traversable wormholes could be stabilized, they might allow instant travel between star systems or even across different regions of the universe. Stabilizing a wormhole, however, would also require exotic matter to prevent it from collapsing. Moreover, the intense gravitational forces near a wormhole could destroy anything attempting to pass through it. Despite these obstacles, the study of wormholes continues to inspire physicists and science fiction writers alike, offering a tantalizing glimpse of how space-time manipulation could reshape our understanding of distance and time. Time itself is deeply tied to space-time structure, and its manipulation raises profound questions. General relativity predicts that time slows down in strong gravitational fields, a phenomenon called gravitational time dilation. This effect has been confirmed in experiments using atomic clocks on satellites, which run slightly faster than clocks on Earth's surface due to weaker gravity. If we could control space-time curvature, we might one day create regions where time flows more slowly or quickly, opening the door to applications such as time travel or advanced communication technologies. One speculative idea involves creating a closed time-like curve, a loop in space-time that would allow an object or signal to travel back to its own past. While theoretically possible under certain conditions, closed time-like curves would raise significant paradoxes, such as the grandfather paradox, where altering the past could prevent the time traveler's existence. Resolving these paradoxes might require entirely new physics, such as a deeper understanding of quantum mechanics or the nature of causality. The energy requirements for large-scale space-time manipulation are another major hurdle. Moving a single massive object, let alone warping space-time on an interstellar scale, would demand immense amounts of energy. Some proposals suggest tapping into exotic energy sources, such as zero-point energy or the vacuum energy of space itself. While these ideas remain speculative, they highlight the need for breakthroughs in energy production and control. Spacetime manipulation also raises ethical and philosophical questions. What responsibilities would humanity have in altering the structure of the universe? Could such technologies be weaponized? And how might they impact the fabric of reality itself? These considerations underscore the need for careful thought as we explore the possibilities of spacetime engineering. Despite the challenges, the study of spacetime manipulation continues to push the boundaries of human knowledge. Advanced experiments, such as those at the Large Hadron Collider and gravitational wave observatories like LIGO and Virgo, probe the fundamental properties of spacetime, searching for clues about its behavior and potential for manipulation. Theoretical research into quantum gravity, string theory, and other cutting-edge frameworks also holds promise for uncovering new ways to interact with spacetime. Ultimately, the idea of manipulating spacetime reflects humanity's drive to transcend its limits. Whether by enabling faster-than-light travel, creating gateways to distant galaxies, or unlocking the mysteries of time, spacetime manipulation represents a bold frontier of exploration and discovery. It challenges us to imagine not just where we might go, but how we might reshape the universe itself. Could spacetime one day become a canvas for human ingenuity, as much a tool as it is a backdrop for existence? The answer may lie in the distant future, but the journey to understand and harness spacetime is already underway. If you like the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.